Hi everyone, good morning. Welcome. I hope you have a very nice weekend. Did anyone figure this out? Did you take a look at this, figure out if you can order a large cappuccino in Te Reo Maori, which is, the indigenous language in New Zealand? Anyone? You can maybe figure it out. You spend like 10 seconds looking at it. What's the Maori word for long? You might look here. Does it show? So if you look at these two, they'll have a short black, and the only thing that's different between them on the Maori side is these two. So most likely roa is the word for long. Anyway, what I wanted to show you with this exercise, you have the slides, right? So you could actually find it, is that two things. First of all, parallel data, the type of those that you see here, right? Translations of sentences are a very, very common thing. Humans produce these things naturally, especially in multilingual, multicultural societies. And the second thing that I wanted to show you was that humans would be able to answer these questions very easily, or with a little bit of effort, let's say. I'm pretty sure all of you could answer those questions using, 1, 2, 3, 4, 5, 6, 7 parallel sentences. Okay, parallel sentences are the ones, translations of each other. You give these 7 parallel sentences to a computer or to, a language model or whatever, and you try to ask it those same questions. You're very likely to not be able to figure it out, right? So humans are very, very efficient at being logical about, figuring things out when it comes to language. So anyway, today's lecture will be centered on machine translation and multilinguality. I'm Antonis Anastasopoulos. I'm a professor at George Mason University, which is in North Virginia, close to Washington, D.C. in the States. I've been working on machine translation and on building NLP in multilingual settings, mostly for low resource languages, for endangered languages, for indigenous languages, for dialects, and so on, for the best part of the last 10 years. So this is really what I'm mainly working on. I really do not want to just speak by myself for an hour and a half and then another hour and a half later. So please, whatever is unclear, raise your hand, ask. If I ask a question, feel free to, engage, entirely up to you. Okay, so let's talk about machine translation. So what is machine translation? Oh yeah, so I guess the big things that I want to cover in this first half are these. We'll start with a historical note, and then we'll talk a little bit about current approaches and how we're going to evaluate machine translation. Right, okay. So what is machine translation? Machine translation is the task of obtaining input in one language and then automatically translating it in another language. The terminology in the field is the source and the target language, and the important thing when we do this process is that we keep the meaning the same, right, or as close as possible. So, if we're given this French sentence, which I will not try to pronounce, then, and we want to train a model that can potentially produce this English one because it means the same. Now, why would we even do this? Again, this has been the classic test of language understanding, meaning that if you think about it, in order to perform this task, you need to be able to do 2 core things very well, right? The first is you need to be able to understand this source sentence, right? You need to be able to completely, somehow represent the meaning, or, you really need to understand the meaning. And then you need to be able to convey that meaning and generate language, possibly, in another language to produce a grammatical sentence that conveys that meaning. So it has been one of the major focuses, plural of focus, of NLP research all the way since the 40s and the 50s. And in general, as a industry-wise, this is a very big industry. It's a $40 billion industry, a year industry. It's very much still big in Europe for perhaps obvious reasons. It is still growing in Asia, a little less in the US, but and there's very large social, government, and military commercial needs. To give you an example, almost all of research on machine translation in the US, at least, through the 60s all the way to the 2010s, was mostly funded by the military in the US. And the important thing is that, again, as I said, humans produce translations naturally, right? You go to a website like the United Nations, and you'll be able to find parallel data in all 6 of the United Nations official languages. Or you might remember that we translate books across languages. Here's the most translated book of all time. Here's the second most translated book of all time. And again, this is something that what is it? Publishing houses pay a lot of money to do. It's something that humans do naturally. You might also think about all of the different domain-specific settings where you might be translating, from one language to the other. From your local Chinese restaurant to maybe think of the big company that produces washing machines. And then they need to translate the manuals for those washing machines to all of the languages of the countries where they sell their washing machines to. So overall, again, the numbers for why do we even care about machine translation is that even Google Translate, through their free API, they translate 100 billion words a day. They translate a lot more through their paid API. Even if you think of social media, companies like Facebook developed and still have research teams that work on machine translation, exactly because, if you're in the business of facilitating communication across people, then you need to be able to do this also across languages. And there's another very interesting example where even eBay, the big e-sales, I guess, e-commerce, I don't know how to describe it, company, they did a study and they showed that when they rolled out English-Spanish translation for some of the products that were sold between the US and Mexico, that actually increased cross-border trade. Basically, it facilitated the sales of Mexican products across the border in the US just because they enabled the automatic translation on some products that they did in A/B testing. So, it's important, and it's still important. I don't know if you actually discussed this, but machine translation has also been the flagship task for the development of deep learning techniques. You've already talked about recurrent neural networks, right? And encoder decoders, yes, and the attention mechanism, right? And transformers. Now, all of these were originally introduced in the context of machine translation. Okay? They have been since appropriated for language models and large language models and all of that, but they were originally developed to perform machine translation. Right, that's what this says. So what I'm going to start first is talk a little bit about the history of the field, and then we'll go into methods. So machine translation really started as a field in the early 50s, right after the Second World War. And at the time, they were using rule-based techniques. So there's this famous Georgetown IBM experiment. Georgetown is another university in the DC area, where they showed how they got a bunch of linguists and maybe a couple of computer scientists, and they sat down together and they wrote rules about how they could potentially translate Russian into English. And the flow charts of the rules look like this. This is just a small part of the rules that they had developed, right? It's not the whole thing. But it was really the first demonstration of I don't actually know if it was viable, of a machine translation system. They used dictionaries and then mapped parts of the sort, because Russian is morphologically rich and words change. So they had a bunch of rules on how to put things together in English and so on. So it was obviously very complicated. This clearly would never scale up to something that would be able to cover a lot of languages and in all of their depth. But I just thought I'd put this out there. Now, since then, things changed a lot. In the 90s, all the way till the 2010s, let's say, we moved from rule-based approaches to ones based on data, right? And that's what statistical machine translation means. And the core idea is that we're trying now to learn a probabilistic model from data. And the setup is the following. Let's say that we're trying to translate from French to English. And what we really want, let's do this at the sentence level, even though we don't really have to. We could do this at the document level, at the paragraph level. Everything would be exactly the same. It's just sentences are an easy unit to think about. So really what we want is to find the best English sentence given some foreign sentence. And a lot of the work at the time was inspired by the process of decipherment. What is this? The Rosetta Stone, right? So it's what actually facilitated the decipherment of the two ancient Egyptian scripts. So this stone had effectively fragments of the same text in both Egyptian hieroglyphics, Egyptian Demotic, and ancient Greek. And even though we had lost the capability to read and understand ancient Egyptian, Champollion was able to figure out the associations between the two parts of the text exactly because they were translations of each other. And that facilitated the decipherment of the script and then the understanding of the language and so on and so forth. And now we're able to read basically almost everything that has ever been written in the ancient Egyptian. So what Warren Weaver, the pioneer of machine translation, allegedly said in 1947 was very much inspired by a very similar process, right? So they said, look, you give me a sentence or an article in Russian, right? But really, I'm going to assume that it was not originally written in Russian. It was originally written in English, okay? And someone went ahead and, encoded it or, used a cipher to present it to me in these strange Cyrillic symbols, okay? So what I need to do is decipher, right? Undo this process, this cryptographic process that hid the message that the author originally was trying to say. And fun fact, who has heard of the Navajo translators? So, okay, there's one hand back there. So basically, in the Second World War, okay, the Germans had Enigma, all right, and you all kind of know the story. The Americans at some point, especially in the Pacific Theater, to facilitate secure or encrypted communication, what they did is, it's not exactly great because, they forced people to do this, but they took Navajo Native Americans, right, who spoke both their own Diné language and English. So they had these people operate the, not phones, whatever it was they used to communicate, across different places. The English-speaking commander would convey the message to the Navajo speaker. The Navajo speaker will speak the same message and send it in Navajo, in Diné, to the other Navajo person, and then the Navajo person would translate it back in English for the other commander in a different place, right? So effectively, they did use translation as a means of encryption, and because Russians didn't have access to, Navajo speakers, then it was actually very, very effective. And that's why, back in 47, people were still thinking of translation as in terms of like decryption. So what would this look like? Let's say we have this model of, we want to find the most likely English sentence for this weird foreign sentence that someone is uttering to us, is telling us, right? We have this confusing foreign sentence and we want to find the most likely English translation. The idea is, again, that this English sentence here was originally conceived in English. Like the thing that you heard was originally conceived in English, right? And it came from, with some probability, sampled from an English language model, right? And then someone put this through a blender, okay, or a cipher or whatever, and then produce this confusing foreign sentence. And what we want to do is recover, the original one. Perhaps you might have seen this, but this is just a straightforward application of the Bayes rule, right? So again, what does this say? And that's the model for the noisy channel machine translation approach. This is saying, I want to find the English sentence E that maximizes the probability of this, given this model, given this French sentence, okay? Oh, welcome, good morning. Now, if we apply Bayes' rule here to this conditional probability, we end up with this equation, which is just straightforward application. And because what we care about is the argmax, the highest scoring E, the denominator doesn't really matter, right? So we can drop it and end up with this equation here. So now notice that we have two things, right? We have the English language model here, okay? And then we also have the translation model that goes the other way, right? So if you remember, this is, again, here, the English language model, and this is the translation that goes the other way, okay? And what do these two components do? The language model will make sure that the translation that we pick is going to be fluent, grammatical, right? Because what do language models do? They score sentences and they tell us whether a sentence is likely or not likely, right? You have talked about this. And it can be, it used to be at the time that these slides were written, it used to be like an Ngram model. Today it's going to be a neural model, or in fact, today we're not even going to use this approach, but it's never mind. So it's going to be any language model. It doesn't really matter what it is. And then the translation model, what it's going to do is it's going to give us a translation probability, and it's going to ensure the adequacy of the translation, right? It's going to ensure that, we convey the same meaning, and we don't just produce, a nice sounding English sentence that is otherwise completely unrelated to the source that we were given. So let's say we have a translation model, and what we want to obtain is we want to have a translation model P of F given E that will give us the probability of translating this English sentence into a foreign sentence. Notice now the directionality is the opposite. And let's say if we have this French sentence, what we want from a good translation model is to give high probability scores to good translations, like the first two, and very, very low scores to a bad translation for this sentence, right? So how are we going to do this? You could say, hey, I know how to compute probabilities. I'm going to count all of the events and then divide by the total sum of the events, right? But obviously, you cannot do this at the sentence level, right? You cannot enumerate all possible sentences. This is going to be very, very, very sparse. And this obviously will not generalize to new inputs. So just like when we talked about language models, well, when you guys, I guess, last week talked about language models, we don't compute probabilities at the sentence level. We break down sentences at the word level, right? And we're going to do exactly the same thing here, and we're going to do lexical translation, right? That's translation at the word level. And, the first thing that, if I ask you, how are we going to translate a word? The first immediate answer could be, well, we're just going to look it up in a dictionary, right? People have been building parallel dictionaries across languages for centuries, really. So let's say you have this German word, house, and we look it up in the dictionary, and its possible translations are house, home, shell, and household. And notice already that we already have a problem, right? It's not like we can always, for any word, pick another word in another language and call it good, right? So there's ambiguity, there's potentially different registers that we need to take into account, not to mention for many languages there might be different inflections. And then all of these are also different, right? So house and home are two very common translations. Shell is a specialized one. In German, you would use house for the shell of a snail, right? And others might be even more, and others like household might, again, really depend on the context. So ideally, right, we would be able to know how common each of these things are, right? So let's say somehow we were able to obtain counts of how many times was the German word house translated into each of these four English words, right? And somehow we got this number. Okay? We went through a bunch of books that had been translated, and we found that 5,000 times out of 7,000 something, house was translated to house, and 2,000 times it was translated to homes, to home, okay, and so on. So if we had this, we could very easily compute this translation by just for example, doing 5,000 divided by the sum of all of those, right? That's just straightforward probability. And that would be exactly what you'd get from maximum likelihood estimation of these probabilities, right? The problem is, no one goes around like, even if you have translations of things, right? They are never annotated with links between all of the words that will allow you to compute those counts. So really what we want is, eventually we'll get to computing those. So what we want, again, is a model that will, if we have English and French sentences, right, each of those with a certain number of words, we want to, or we're going to have to make the following assumptions. And that's the simplest type of assumption that you're going to make that will try to explain how these two parallel sentences came to be. Okay? We had a source sentence, F, and we're going to tell the generative story of how this English sentence was produced. And we're going to make the assumption that each of the English words was based on one French sentence, okay? Because we're doing word-to-word type translation. This M here, by the way, is just the length of the English sentence. It's there for completeness. It doesn't particularly matter. Okay? So if we say that each English word was produced by a French word because of a certain French word on the input, okay? What it implies is that there's an alignment between the two, right? This English word is connected to this French word. And we can denote this with a variable. And here's the nice idea. If we have these alignments, then the decisions of the words are independent from each other. I'll show what this means in a minute. So putting these together, what we're going to have is a decomposition of the translation model to introduce this latent variable of the alignment, right? So what we're going to have is we're going to have the source French sentence. We're going to choose a length for our output. Again, doesn't really matter. And then we're going to say, well, for this French sentence, we're going to select the alignments. And now, when we have the French sentence and the alignments, then we will select the words. And put these two together, we're going to end up with an English sentence. So what is alignment? It's, again, the alignment is this correspondence between particular words in a translated sentence pair, right? So you might have the English sentence, Japan shaken by 2 new quakes. You might have the equivalent French sentence, and you might notice that, English and French align very, very nicely, one word at a time. We do have another spurious word in there that doesn't really align to anything, but that's okay, because we're going from French to English, right? But each of the English words are aligned to exactly one French word. So this setup here, this alignment setup, was where most of the action in at least 10 years of statistical machine translation was, right? It wasn't that, hard to get possible words translated. It was their ordering when you go from one sentence from one language to the other that it was the problem, and what was what we actually had to deal with modeling. So let's visualize this by drawing those links, right? Let's say we have this German sentence, das Haus ist klein, which means the house is small, and the way that, again, we assume that this English sentence was produced was, we chose those alignments here. We said they're going to go this way, right? And we can denote them with the vector. Like this says that the English word in position 1 here aligns to the German word in position 1. This says the English word in position 2 aligns to the German word in position 2, and so forth. Okay? And it could, of course, the problem is that across languages you might have reordering, right? German sometimes puts the verb at the very end of the sentence, as opposed to always between the subject and the object, or not always, but you know what I mean, like English does. Adjectives and nouns go in that order in English, but they very often go in the opposite order, noun and adjectives, in Spanish, for instance. So the problem is reordering, right? You cannot just go word for word, produce translations, and assume that you're going to get a good translation in another language. So here's another possible translation, right? Maybe the English word in position 1 was produced because of the German word in position 3, right? And this is what this says. Or the English word in position 2 was produced because of the German word in position 4, and so on and so forth, right? That's another possible alignment. It's not a good one, but it is a possible one. Sometimes you might have things that don't get translated at all. Right? So, if we translate into a shorter sentence than the source one, it is likely that, there's going to be a sentence that is not, a word that is not translated, and that's okay, right? What we require is that at least each of the English words are aligned to exactly one word, right? You might also have the opposite, right? You might translate into something that is longer in terms of words than what you already have, but we did say that we need to have each of the words accounted for, and this is not just about length. You might just have additions on the English side that don't really exist on the German side, right? Here, the German sentence doesn't really include this just, but maybe the translator put it there because they thought it worked well in the context. Nevertheless, we can still deal with it. What we did is like this little trick of adding this null token in the beginning of the German. And we can still do something like this. We can do one-to-many translation. That means that we can have two English sentences appear because of the same German word. Okay, that's okay. What we cannot do, and again, we would, that's what the alignment vector would look like. What we cannot do is the opposite, right? Because we didn't really, it's not part of our assumptions, right? We said that each English word is only going to be because of a single German or French word, okay? So we cannot do this type of many-to-one translation. And you might see already the problem, right? How would you even write a vector the way that we've been writing it so far? This would be a little problematic. So putting all of these things together will create the famous IBM Model 1, which was the very, very first simplest lexical translation model that made the assumption that each of those alignment decisions are independent from each other, and then that there's a uniform distribution for each of the alignments over the source words. That's, again, not particularly important, but let me show you how you would use this lexical model to translate, okay? We have a German sentence, okay? This now includes the null word that will allow us to also potentially create new words in English if we need to. And what is the first thing that we're going to do is we're going to create alignments, okay? So let's say we create these types of alignments because we think that's a decent alignment for this German sentence. And then given these alignments, now we know that we have to pick an English word that was produced because of the German word das, right? Das is an article, then maybe we can pick the, okay? Then, we have the second word, house. We already looked it up in the dictionary, right? A good translation is home or house or shell. We're going to pick house, and so on and so forth. The last thing that we're going to do is score this output English sentence with the English language model, Okay? And the English language model is going to give it a high score because this is a well-formed grammatical English sentence, and that's great. So the language model will say, yeah, that's a good sentence, right? We could also pick a different alignment in the beginning and then sample for complete sake, for simplicity's sake, the same words, and now we would end up with this sentence: house is small d. Right? But thankfully, the language model, which we already have from before, right, will say, this is not a really good English sentence, low score. Okay? So the way that we would translate, if we have this alignment approach, right, is compute all of the possible alignments, right, all of the possible reorderings, sample words, and then score them with a language model. And each of those, out of all of those, we're going to pick the one with the highest probability, and that will probably be a decent translation. Okay? That's a very simple approach. It's surprisingly, I don't know if it's surprising, but it works, right? We added a lot more complicated alignments over the years. Really, there were like 15 years of research on how to do this and how to do reordering better. But at its core, it's still the same type of model. So, again, here's the problem. No one actually sits down and produces these types of alignments. Okay? So how are we going to even learn these parameters, right? We can look things up in the dictionary, but they don't tell us how common things are. Okay? What we do have when we start is just translations. We have parallel sentences, and we might have an abundance of them, right? Because, again, humans produce them at scale. So it becomes a bit of a chicken and egg problem, to which we will come back later as well. So let's think about it. If we have parallel translations, right, and someone sits down and draws those links between all of the possible words, right, then we can just count up along those links and perform maximum likelihood estimation and just obtain the probabilities for each English word given a French word. Okay? Unfortunately, we do not have the alignments. Now, conversely, if we did have translation probabilities, right, somehow, then we would be able to just align everything and compute those links between the two sides of the parallel data, right? The problem is we have neither, right? We do not have alignments. We do not have the parameters, right, the lexical translation probabilities. But if we had one of each, we would be able to compute the other, right? Hence the chicken and egg problem, okay? Fun fact, eggs did become before chicken, right? Like everybody agrees on this. Okay, so, yeah. Okay, so now this brings me to the one of the most magical, that is not really magical, you can prove why it works, things in machine learning called the expectation maximization algorithm, or EM for short, which not very people use these days, but I think it's a very, very, very cool thing. That's why we're covering it today. So here's the idea, okay? Again, we have alignments and parameters, and each of those, if we had one of those, we would be able to compute the other, okay? So what we're gonna do is we're gonna pick some random, or in practice, uniform parameters. And given those parameters, the initial random ones, right? What we're gonna do is we're gonna do an iteration of the following. We have some random parameters, and given those, we're gonna estimate the alignments. Right? Now, given those alignments, we're going to go back and re-estimate the parameters. And then we're going to do this a few more times. And at the end, when we do this, we're going to end up with good alignments and good parameters. Okay? And the reason that this works is because there's a mathematical proof. It provides the solution to basically doing gradient descent on the whole likelihood of the data. But again, what we're going to do is using the current parameters, we're going to compute expected alignments. And then we're going to keep track of these expected number of times that a word translates to the other. I'm going to show you an example in a minute. And this is the E step, the expectation step. And then now that we have the expected alignments, what we can do is count them up and maximize the probabilities for the parameters that we have here. And that's the M step. Okay? And that's why it's called the EM algorithm. In practice, it's a set of iterations of E, M, E, M, E, M. And at the end, we're going to end up with like good a good model. Let me show you the example. It's not intuitive why it works, but when you see the example, you'll get it. So let's say we have this very, very, very simple corpus, okay? 3 parallel sentences between French and English, okay? We have the house and la maison, we have the blue house and la maison bleue, and then we have the flower, la fleur, okay? And initially, we're agnostic about what can potentially, connect to each other. All of these alignments, we draw them up. All words see here connect to all words. And each of those alignments are all equally likely, all right? And let's count up real quick. How many times has the word the be aligned to each of the French words, okay? Each of these alignments are equally likely. So let's see. We have the aligning to la. How many times? 1, 2, 3. Right? Yes. So let's put it here. Let's say la. 3. Okay. How many times did the align to maison? It's only 2, right? Through this one and this one. 2. How many times it aligns to bleu? It's only this one. I cannot really write here. There's too many screens. Sorry. It's just 1, right? And it's just 1. And then for fleur, it's going to be again 1, right? So now you have those counts now. Okay, they're not going to be actual integers in practice. They're going to be fractional alignments, but it doesn't really matter, right? So now, if you count these things up and you say, okay, now the probability of the given la is going to be, the probability of la given the is going to be 3, right? Divided by the sum of all of these, which is going to be 3 over 7, okay? Which is already closer to, it's higher than 1 over 4. Which is what we started with. Because initially we said if we have 4 words, they're all equally likely, right? So it's 1 over 4, and this is 3 over 7. So it's already better, right? It got better. So we did 1 iteration, and now these connections between la and the became a little more likely than what they were before. And the connections, for example, between maison and house also maybe became a little more likely, and so on and so forth. So we do another iteration. These will become now a little bit more likely as well as we keep going, right? And notice now how, if this is very, very likely, right, we can start applying something like the pigeonhole principle and say, look, I have 2 sentences with 2 words each, right? And I know that these 2 are very, very likely aligned to each other. This should also mean that now these 2 are also very, very likely to align with each other. Yes? Right? Makes sense. The same here, right? So again, as you keep going through those iterations, these will become more and more likely, and eventually these will become more and more likely than that were initially. And then at the very end, you're going to end up with something that will look like this, okay? In practice, all of these other alignments between will never disappear unless you run the model, all these iterations to infinity. But in practice, they will become very, 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 very likely. Okay. And now, if we have these, now we can just count how many times la was aligned to the, or how many times le was aligned to the, how many times maison was aligned to house, and so on. And now just count these things up and obtain the parameters of our lexical translation model from these now aligned corpus that we obtained. Okay? So we started with uniform alignments. We computed some parameters. We started the other way. We started with uniform parameters. We computed some alignments. We went back to the parameters and so on and so forth. At some point, ended up with a somewhat stable or a very stable setup for the alignments. And then we used that to obtain good alignments and then compute our parameters for the model. The parameters being just these probabilities that will give us which word translates into which one. Okay? And all we had initially was not a dictionary or anything. All we had was parallel sentences. And we made the assumption that words connect along those sentences, 1-to-1, basically. And yeah, so this is, again, an example, not the same example. Now it's German to English. Again, you have 4 words in German, 4 words in English. So all of the initial probabilities are like 1 over 4, okay, 0.25. But as you do the iterations, and perhaps this is something I invite you to do this by hand if you really want to, you can see how right away from the initial iteration, some things will become more likely. They become 0.5 from 0.25. And then that will eventually cause these to keep increasing, so that eventually, finally, if we, again, run it, infinite iterations, we will end up to 1, and others will now start decreasing until they become 0, exactly because we have a very, very, very sparse corpus in this case. In practice, these will never, again, end up being 0 and 1. Yes? Okay, pause. I am legally deaf. I am just too young to accept it, so I'm not wearing hearing aids. So just speak louder.
Okay. What about der, die, das? It all translates to the.
Yes. So this is you're absolutely right. In German, the question was, wait, in German I don't have one definite article. We have 3 because there's 3 grammatical genders in German, right? And in fact, you don't only have das that could be translated to the. You also have die and der as an example, right? In fact, you could also potentially, going into English, you could also have des and dem and all of these, because German. But the answer is, first of all, these become 1 and 0, and this is just a toy example, right, where we only have das. In practice, what you're going to have is a really, really big corpus of parallel sentences, and the model would learn that all of these are very likely translations of the, or the other way around, all of these could potentially be translated very likely into the, right? But yeah, ambiguity will always be there, okay? We're never going to end up with something being very, very likely unless you are in this rare case of, a single word always being translated one way in exactly another very, very similar word. Okay? Any other questions? So again, this is just one component, right? This is what allows us to learn the lexical probabilities at the word level. We still have to put all of these things together and produce then potentially good alignments and then sample these words. I just wanted to show you how from just parallel sentences, we can effectively obtain alignments, and that means a probabilistic dictionary, let's call it this way, right? Which is basically what it is. Okay, so now let's talk about how no one translates at the word level, right? We all think, and we agree that language works this way in terms of phrases, right? So really, if we have obtained an alignment, here denoted with these black squares, that denotes that, Michael translates to Michael, translates to get von aus, there's a comma that is untranslated, and so on, right? What is a phrase? And, if you're a linguist, you might say a phrase is, a constituent or something. You haven't talked about syntactic parsing, right? Yeah, very little. But basically, different people will have different definitions of what a phrase is. But a very simple intuition is that phrases are contiguous spans of words. And in our case, we care about phrases that translate into each other, right? So if we know that assumes translates to get von aus, okay, and that translates to das, then you could say, hey, I'm going to expand this and say that assumes that translates to get the von aus, comma, because it exists here, das, right? Or if you wanted to say that Michael assumes is a phrase, then the equivalent German will be this. Michael get the von aus. Okay? And basically, the idea is now we're going to use these word level alignments, and we're going to keep all of these things that appear contiguous on both sides, like this one, or even just this one, right? And call these phrases. Yeah? Can I? Why not? I can, right? So they have to be consistent, right? We cannot just leave things out if they, align. and don't worry about all of these. They're here for completeness. The intuition is, you have to pick squares. Let me go back. They have to pick squares that are contiguous on both sides, and there's no additional black squares outside of them along these same rows and columns. Okay, that's the simple intuition. Okay, so now when we have that, we're gonna start with word level pairs, and then keep expanding by expanding the size of our boxes, and then in the end we're gonna end up with all of these pairs of phrases from a single sentence pair, right? And in fact, what's the biggest phrase in this case? It's the whole. You think of the whole sentence as a phrase, it will still also be in there. It will be, this big box satisfies all of the requirements that we set for a phrase. So now, again, over a very big corpus, again, we can now compute how many times these phrases were translated into each other, and we can go back and now compute phrase-level translation probabilities. And if we have those, that means that now we are not operating at the word level, but now we're operating in chunks, right, in phrases. So this leads us to phrase-based MT, which was the approach that powered tools like Google Translate all the way until 2014. Okay? I don't know if you remember Google Translate in 2014. Some people would say it was terrible, but it was usable, right? People used Google Translate. As an example, right, there were other companies that had good translation systems as well. But people used Google Translate in 2013 and 2014 before, the neural revolution happened. But basically the core idea is now if I have a source sentence, let's say in this case, this Spanish sentence, I'm going to split it up into phrases. The phrases that I might be able to find in this big phrase table that we created before that are associated with probabilities, right? Which we extracted from the word level stuff. And, one phrase is Maria, and this can be translated to Mary according to our phrase table. No can be translated to not or no. But then we also find another phrase that is no dio, which our phrase table translates to did not give, right? Or we might have una bofetada, which is a slap that can be translated as a phrase. Notice that this can also be translated at the word level, one by one, right? Or you might have an even longer phrase like dio una bofetada, that is kind of like slap or slapped, right? And then so on and so forth, right, through the whole sentence. So any of the phrases that you find in this Spanish sentence, you will, put this into this lattice here. Put this into this lattice. And then quotes, all you have to do is now find the most likely path through all of these options that produces the most likely translation, right? And how are you going to do this? We go back to the language model, right? We're going to score all of the possible paths, and maybe the language model that we have in English will tell us that the most likely path is the green one here. Mary did not slap the green witch. And, that's going to be the output that we're going to return from our translation model. So what did we do? We started with parallel sentences. We identified good word level probabilities, translation probabilities, and alignments. Then we used those alignments to expand into phrases. We computed again phrase level probabilities, and then using those, we were able to construct this type of lattice and then just search through all possible paths in this lattice to produce a decent translation. And that, at its core, is how statistical MT worked. Any questions? Okay, great. So there was another paradigm kind of like developed somewhat in parallel, which was syntax-based MT. And it was the idea that rather than operating at the word level or at the phrase level, what we really want to do is incorporate syntax, right? Which, defines for every language how the language puts words together to construct phrases, right? And you construct these types of trees. And maybe what you really want to learn is not associations between, word symbolic phrases, but you want to learn associations between trees or subtrees between languages, right? You might want to learn that, an adjective noun phrase constituent type thing in English, all you need to do to translate is flip the order around and make it a noun adjective noun phrase when you go into Spanish, for instance. And that's a generalized rule that you can apply in any noun phrase, when you go from English to Spanish. Again, I'm oversimplifying, but that was the core idea, right? That we operated now over syntactic trees instead of operating only on the symbolic word level. Nevertheless, it was very hard to make work. It was maybe state of the art for 1 year until it was much easier to deploy phrase-based ones. Now, here's what happened in 2014. Neural approaches were developed for machine translation, and everything changed. Basically, you have already talked about neural models and the encoder-decoder and everything, right? So what happened then was people proposed a way to learn a single network, right? An end-to-end approach to go from one sentence in one language to another, right? Using neural networks. It was, the sequence model. It doesn't have to involve two RNNs. It could be two LSTMs. It could be two attention-based two transformers or whatever. This is like a slightly old slide. But basically, the important thing is that the previous approach, the phrase-based one that everybody used, had a lot of little moving components, right? We had to start with an alignment mechanism, and then we had to figure out how to go to phrases, and then we had to figure out other little things like reordering, and we had the language model on top of all of these, right? And there's a lot of little components that you had to make work with each other. Here, what you said, and when you talk about the encoder-decoder model, is that just give me examples of input and output, and I'm going to have a powerful neural network that can just learn the mapping function from this input to the output. And with enough training examples and with enough parameters and with enough training of the model can learn at this function, can learn to approximate this function. Okay? So that's the beauty of the neural approaches, is that really what you have is this universal approximator that as long as you give it examples of inputs and outputs, whatever function it is. It might be a function of going from English to Swahili, or it might be a function from going from a bunch of data to a label, or whatever it is. You give it enough examples and enough compute with enough parameters, and it will learn to approximate it. So I'm not going to go too deep into reminding you what you guys talked already about, but basically these are, again, just language models. The only thing that's different is that they're conditional, right? You talked about language models, defining them as something like P of Y, right? And you said each of these, oops, that's a J, equals to 1 to J is just the P of Yj given Y1, Y2, Yj. Sorry, I apologize for my terrible handwriting, right? But basically we said, look, we're just going to break down the probability of a sentence, Y, right, into the probabilities of each individual word. And each word is going to be dependent on all of the words that came before it. Okay? That's what we said for language models. The only thing that's different here is this extra added context, this X, that we are given some additional context. In our case, which we're doing translation, is going to be a sentence in another language. Okay? It could be an image. It could be, and then in that case, we would probably be doing image captioning. It could be an image and another caption in another language, and in that case, we might be doing image caption translation, right? But it doesn't really matter. As long as we have an encoding function that allows us to represent this context with some vector and provide it as part of our context, then we can just sample from this language model. The only thing different is that it is conditioned on this added thing. So this was one very simple type of this conditional language model that you already saw, the encoder-decoder. In this case, this is an LSTM encoder-decoder, where the decoder side looks exactly like a language model. And that's exactly what it is. It's a language model. Okay? It produces the probability of the next word, one word at a time. The only thing that's different is that this initial state here is provided, or it's somehow influenced by this whole other thing that happens on top. And what happens on top is that I have another representation function. In this case, it also looks like a language model, but that's not particularly important, right? That gives us a vector representation of the source sentence. In this case, the source sentence is Japanese, and it means I hate this movie. And now we have a representation of this context, and this allows us to condition our decoder, our language model, and train the model to produce not just the language model to produce not just a fluent sentence, but a fluent sentence with the same meaning, right? As long as we train it on such data. So again, you have seen these sequence models before. Again, this is a very simple setting with RNN encoders and decoders. Again, it doesn't really matter. I firmly believe this. As long as you have enough parameters in your neural network, it will learn the function that you're trying to learn. In this case, translate from one language into the other. The only thing that kind of does matter is that some network architectures are more efficient than others. For example, the transformers ones that use self-attention that you already talked about, right? Yes. They take advantage of our current hardware so much better than these linear RNN approaches, and that's why they are the current state of the art. Right, and this is also, again, a reminder of how these things are trained. You are given a source sentence, you have the target sentence, and then you predict one word at a time, and that's what you get your loss from. And again, this is optimized a single system. It's end-to-end. Right, okay. And then, this is not state-of-the-art. The standard approaches use the transformer approaches, the transformer models with self-attention, and then for these representations, and self-attention for this, and also cross-attention between the two. But again, it's fundamentally the exact same thing. It's just a slightly different function for representing the context and for providing it into the decoder. So why does this work so much better? Well, it's because we have a much better language model. Neural language models are better than what we had before. It does make better use of context because we can provide it in every word, potentially, output. And because it is representation-based, rather than relying on the symbolic representations of the words, right? To the computer, when you give it the word house and the word home, there's no information as strings, right? There's no information in there to tell the computer that these two are very, very similar things, right? So what we do when we move into the neural space is we represent all words and really everything in a vector space with a bunch of numbers, right? And if we learn them well enough, these numbers for things that mean the same thing are going to be very, very similar. So this allows us to leverage this vector space representation, both for word level and for phrase level, even sentence level, to be able to account for these similarities. So now, you might have never seen, not never, you might have very rarely seen the word household before. But if your representation for that word is very close to home and house and apartment and all of the other possibly related words, you can kind of get its meaning if you are a neural model. The exact same way that if you're reading a book, right, and you have all of the context and everything, and then suddenly you encounter a word that you don't know, you have never seen it before, you can still kind of get its meaning. Yes, you can. It would be much easier if you actually look it up in the dictionary, but you'd be able to infer the meaning just from the context. And another important thing is that these neural networks can be optimized end-to-end. They don't have all of these little subcomponents that need to be individually optimized and then made to play well together with each other. And you could argue, although if you pushed back on this, I wouldn't fight you back, is that it requires less human engineering effort in the sense that all you need is to define your neural network and then train it, and then hope that it kind of works, which it kind of will, as opposed to building all of these little components and then making them work. And something that is very, very nice is that we can use this very generic method for any language pair, which was not the case with the previous models. We'll talk a little bit about it in the second part of this lecture after the break when we talk about multilinguality. So what are the disadvantages of this new approach? It's definitely less interpretable, right? We're operating in multidimensional spaces with a bunch of numbers, right? And we don't know necessarily what these numbers mean. That makes it kind of hard to debug. It's difficult to control. We cannot go and say, I want you to always translate the word, I don't know, household to whatever is the proper German word. And we cannot have specific rules or guidelines, which might lead to potentially safety concerns. Okay, so any questions so far? Okay, so now let's talk about how are we going to find the most likely translation when we have such a model, right? And I think Saturday, you guys talked about a way to search a structured space, right? You talked about CRFs. And what did this look like? We said we're going to have, for each output position, right, we have a set of possible labels, right? And there were, I don't know, there were some possible labels, right? And then we had these for all possible positions, right? And then we had a start and an end, right? And then we computed all of the connections between them. There were some probabilities between all of these. Okay, I'm not going to draw all of them. And then we said, look, we're going to search through the whole thing. You discussed some efficient algorithms for doing so. And when we have all of these, I'm going to find the most likely path through this thing, and that will be the thing that I return, right? And at the time, you did this where the input was a sequence of words, and maybe the output was either part of speech tags or named entity tags or something, right? It doesn't really matter, whatever it was. So here's my question. Can we do something very similar for translation, right? This is an exact search. It will find the most likely path through this exhaustively listed set of possible paths, right? So can we do this here? Who says yes? Okay, who says no? Why not? Why not?
Probably because we have the alignment problem here. I mean, a word won't have the meaning, won't align with the word that we want to translate to.
Okay, so the way that you define CRFs, right? You had for as many input words, you had as many output positions, right? So that can be one potential problem here in translation, right? There's no guarantee that 12 words in English are going to correspond to exactly 12 words in Italian or Greek or Finnish, okay? So that's one problem. So let's say, so one problem, to generalize, one problem is length, right? The CRFs that you discussed are of fixed length, okay? Here, translation can be anywhere from, smaller to longer, right? Let's say I define a maximum possible length, okay? And, I add a bunch of connections here that go from like end of sentence. So I have this extra thing that I might have that will allow me to, generate a shorter sentence and then just, pad it to make it simple to deal with and go to a maximum length of like 160, something obscene. Will I be able to do this then? Who says yes? Who says no? Well, you should take a hint from Ian, but like, why not? Yeah, why not?
What about normalization? Can you compute the normalization of all of these? We integrate and
Yeah. We can use the exact same algorithm that we had before. You can compute the normalization. It's exactly like a CRF, let's say, like the ones you had before. What is the big difference? Yes?
I'm thinking of the problem that
Okay, I didn't catch that.
Christos, there's another one.
That we cannot at every step get the
Uh-huh.
have the optimal solution at every step, because we may need to parse the whole sentence. We may need to reach the end. That's why.
I think we could.
Okay.
Why couldn't we? Behind you. Right there. Yeah.
Maybe this requires a one-to-one mapping that we might not have for...
Yeah, but let's say we deal with this by having a longer one, and then we possibly allow these padding thing
Repeat it.
that has some reasonable probabilities. Yeah.
It would be really inefficient in a way where we have
much more possible combinations now, because we have every word.
Yeah, so if you remember in the CRF space, right, how many possible output labels did you have? If it was part of speech tags, it might be 15, maybe a few dozen if you're unlucky and you work on the Pentry bank. How many possible output labels? What is this dimensionality here? In the case of translation, is the size of what? It's the size of the dictionary or our vocabulary, right? How many words are there in English? No, really, how many words are there in English? A few thousand? Minimum, right? Let's call it millions, okay? And in fact, if you try to count them, then you'd be stuck, because good luck also counting all of the new words that Gen Alpha is coming up with, right? So that's the big problem here, right? That our output space is really, 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 really big. And now it stops being efficient, right? It's a really big output space that we cannot really explore, okay? It's not that we cannot compute the normalizer. In theory, if we had a big enough CPU, we could, right? If we limited ourselves to the vocabulary somehow, to a fixed vocabulary. It's just, and we dealt somehow with the length. You could say, I'm gonna try all possible lengths and return one that is maybe the most likely. It's just way too inefficient. So what we are gonna end up doing, huh? Could we use what, sorry? Could we use characters? That's an excellent question. As our output space, that would reduce the output space, right? We're gonna have 24 or 28, however many characters there are. Add the punctuation as well, okay? We're gonna end up with like maybe 50, 60 characters. Could we do it then? I say yes, okay? We could. What would be the problem then? The length, one. And the other is the transition probabilities between characters at this point lose meaning, right? You're gonna, translation is inherently like at worst, like a word level or morpheme level thing, right? It would be very, very, I think in theory you could. I don't think that anyone has actually tried, because it doesn't match up, right? But in theory you could. So again, the problem is that when you operate at the word level or the morpheme level or at that space, we can approximate this search, right? It's very hard to find the best possible translation, but we can search this space efficiently to find a good possible translation. So this is what we're gonna do by generating through sampling, right? So the approach that we're gonna use is very similar to how you might have discussed that you can generate from a language model. We're just gonna sample, right? While you have not finished generating, right? Which means select the end of sentence symbol as your next symbol, produce the probability distribution for the next token, and then select one from there. That's very generic, right? Now in our case, what we want is we don't want a sentence out of our model, right? We want the most likely sentence. So you could say, hey, as I'm going through the, each position, I'm gonna select the most likely word. Does that make sense? I think it does. It's a greedy approach. It says, look, I want the most likely translation overall. I'm gonna make the best possible decision according to my model in each position, right? So this is what it says. It always picks the most probable next word. Now, is this good? It's okay. It's just, it's not ideal, right? In practice, this will lead to very boring output. And again, selecting the most probable next word at every position does not guarantee that you're going to end up with the most likely translation overall, right? Because one mistake somewhere could lead you astray. So what we're going to do instead, So what we really want to be able to do is like, if you always do greedy, you're going to always keep selecting the best, and you only have one path. So one mistake really can throw you off. So what we're going to do is we're going to try to be a little more smart about it. And what we're going to do is we're going to do beam search. So what this means is you're going to maintain multiple possible paths as you search the space that are all, high probability, right? And then when all of these kind of end with end of sentence symbols, then we're going to pick the best one out of those, right? So it's just, we don't commit to a single path. We're just going to explore our options and see what happens when we're all done to select the best one. So the approach is perhaps better illustrated this way. So let's say we have a translation model, right, an encoder decoder, and the first output word that we're going to generate is, that we're going to give to it is like a start of sentence symbol, right? And then we do one step, and then we obtain the probability distribution for the next possible words, okay? So for illustration purposes, let's say we're going to do a beam search with a size 2, which means that we're only going to maintain 2 possible paths as we search the space. This is just, it's, so that it fits my slide. In practice, it would do a slightly larger number of paths. So we have this probability distribution as possible next words. Okay, we're going to find the 2 most likely ones, right? And then we're going to maintain both of them as candidates. Okay. Now remember how we said that these are still conditional language models, right? So now, because we have a different history, we now need to expand. By the way, each path will maintain its current score, right? So here the score is just given by the probability of these words, okay? Because before we had nothing. So now we have these 2, and what we're going to do is expand each of those, because the choice of that word affects the probability distribution that you're going to end up with, right? So let's say we go to this path, and now we compute the next probability distribution for the next word. It's what you see here on the right. And what are the possible 2 words next? It's like hate and don't. Okay? And each of these have their own score, right? Hate has a score of 0.5. And now the score for this one is going to be 0.12 times the probability of that word, right? Times 0.5, which makes it 0.06. Okay? I just want to explain how these scores came to be. And then we also have this other option. We're going to do the same for this other candidate. We're going to expand it. Okay? And let's say now the possible continuations are hate and like. Okay? So now, if we kept doing this, right, over and over, how many paths would we end up with? Right? This thing is growing exponentially, right? We started from 1 to 2 to 4. Then if we kept doing this, we would end up with 8, 16. So what we need to do is still maintain, keep this efficient. Okay? So what we're going to do is now we're going to prune the candidates and only keep the top 2. And that's because, again, I chose beam search with size 2. So how are we going to prune? We're just going to look at those scores and keep the 2 paths now with the highest 2 scores. So in this case, we're going to, prune these 2. And now we have 2 candidates, I hate and I don't. And now we expand those again. We prune, we expand, prune, all the way until both of these paths end with an end of sentence, right? It might not be at the same time. It very likely won't, but that's okay. And then at the very end, whatever paths we have constructed, they will have some scores. And now we're just going to return the most likely one. Okay, the one with the highest score. Right. Before I go into evaluation, just one more thing, which is slightly important. I don't have a slide for it, but it's important to know. So these scores, right, as we keep adding words, okay, what will happen to them? As we add words, each word is associated with a probability, right, which is a number between 0 and 1. So multiplying numbers that are between 0 and 1 with another number that is between 0 and 1 is going to make it smaller, right? So it is impossible for the expansion of this graph, this path, to lead to paths with higher score, right? Because we multiplied with something smaller than 1. So suddenly you might see that, okay, wait, this means that beam search really prefers shorter paths, right? If I had expanded this, for example, to end of sentence, okay? Even if it was somewhat unlikely, right? But I somehow had ended up with an end of sentence in my beam. But then I had kept expanding this, and I had added 2 or 3 more words. I would have effectively made all of these paths 2 or 3 orders of magnitude less likely, right? So I might have ended up with a beam that, this one ended too early, frankly, right, with an end of sentence. And the good translation, because it's just longer, ended up with a smaller score, right? Do you see the potential problem here? Okay, I see some heads nodding. So what we did, I guess, in practice is called length normalization. So the scores that we keep for every path is not just the score of the path times the word. It's also adjusted for where we are in the path, in the generation, to make sure that we don't end early, because it was a very common problem, and adjust for the possible lengths. Okay? So, yeah, I just thought it was kind of interesting to point out. Yes, what? Yeah.
So this beam search approach where you keep pruning is still greedy, right? Like there's a chance that one of the paths that you pruned, if you had kept growing it, later it would produce a higher probability overall.
You're absolutely right, yes. There's still no guarantee that you're going to actually find the most likely translation. It's just, we usually end up with a decent translation.
Just a little better than
the greedy. Yeah. And in
yes.
practice, what we would do, especially with length normalization, you could do a pretty large beam search of size 5, 10, 50, even 100 with some additional little tricks, and really effectively actually search the space.
Thank you.
All right, I have about 10-ish minutes, so I just want to finish the MT part. So let's briefly talk about how we're going to evaluate our systems, right? Now, here's the problem with machine translation, with translation in general. There's no one single correct answer, okay? There's many ways to express the same meaning in language. Okay, if you have like short sentences, then it's sure, maybe whatever. But nevertheless, there's no one good answer, right? There's many possible good answers. And that is a problem for our evaluation, right? So let's say the first thing that what we will do is we're going to have a test set that is human professionally translated, right, by some professional translators, so that we have at least some reference of what a good translation looks like. Yeah? So in this example, we have some Italian source sentence, and then that translates into and then we have an empty model that produces this translation, right? So a good translation of this Italian would be, I would like a cold cappuccino, okay? Which if you haven't tried while you've been here, you should. It's a Greek thing. If you're Italian, I'm sorry, I know it's sacrilege, but it's good. Okay, so this is a good reference, right? I would like a cold cappuccino. So now, is this a good translation, the one that the EMT produced? You could argue one way or the other, right? It's I like one cold cappuccino is a little awkward, but it conveys the meaning, right? It would be, way better than having something completely that doesn't even mention coffee, right? So the idea of our reference-based evaluation is that we're going to compare the output of our system with the reference that the translator provided, and we're going to try to come up with a score. And if it's exactly the same, then excellent. If it is somewhat similar, then we're going to give it a slightly lower score. And if it's completely terrible, we're going to give it a very low score. So the most commonly used metric still is called BLE, bilingual evaluation understudy, it doesn't really matter. And the idea is that we're going to compare the machine written translation to one or possibly several human written translations, and we're going to look at n-grams, right, and see how well they match between the reference and the hypothesis, right? The hypothesis is the translation that the MT system produced. We're also going to have this penalty to avoid cheating the metric. It's not particularly important. The important thing is that you want to make sure that you cover all of the reference, and it can be very, very useful for comparing systems, but it's obviously imperfect, right? If you have, and that's exactly because there's many valid ways to translate the sentence. If you had translated, I don't know, like I like one to I want one, right? Want and like are two completely different words, right? And when you compare them at the symbolic level, blue is going to say, you didn't produce the correct word, you get a penalty, right? The ideal scenario is that we would operate somehow and be able to identify that want and like in that context is actually very similar. It can, and still be able to score it appropriately. So and that's because a good translation can still get a low blue score because the score, that metric operates at the symbolic level still, right? So here's an example of how this would look like. What you would do is you would compare unigrams and bigrams and trigrams between the reference and the hypothesis. You could compute how, the precisions for each of those, combine them, and report the number, right? That's the simplest thing. But can you cheat this very simple metric? How about this bad translation? I like one cold cappuccino, right? Now, if you look at how many of the unigrams of the hypothesis appear in the reference, suddenly 7 out of the 8 appear in the reference, right? So what's one simple solution to avoid this type of cheating? If we have matched a word to this word in the reference, then we won't allow any other word to match to it, right? So effectively, all of these will be penalized, okay? So that's one slight change we're gonna make to the blue metric. Here's another way to cheat. If we have a very short hypothesis that really very well matches the reference that we have, right? A part of the reference that we have. If you only look at unigram, bigram, and trigram precision, these are all perfect, right? But this is clearly not a good translation. So that's why we added the brevity penalty, so that, if the lengths of the hypothesis and the reference are very different, then we still penalize the hypothesis. And then here's another big problem. Let's say that we have the following hypothesis, okay? I would like a cold cappuccino, so that's the reference. Let's say we have the hypothesis, I would like one cold cappuccino, I would like a cold espresso, and I would like a cold monk, okay? And you would probably agree with me that the first option is the best, the second is still kind of okay, right? Just mistranslated the type of coffee, and the third one is worse, okay? But all of these have very, very, very similar blue scores because they only differ by exactly one word, okay? So really, what the next level of the metric is to try and use synonyms or paraphrases so that, espresso and cappuccino are identified as something similar things, or one and a are identified as somewhat similar things, and use synonyms or paraphrases and all. So this was a metric that did that was Meteor, which was basically like blue, except it took into account semantic similarity between words. At that time, this was still done at the symbolic level. They had lists of synonyms, and they said, hey, house and home basically are synonyms. So if one translation system produces house, but the reference says home, don't penalize it that much, as if it had produced a very, very different word, right? But nevertheless, this is still not ideal, right? Because we have so far only dealt with languages like English and Italian and Spanish. But what happens if you're trying to translate into languages with rich morphology, right? This is an example, I want to say it's either Turkish or Azerbaijani, I'm sorry, I don't exactly remember, where this source sentence, behaving as if you're among those whom we could not civilize, would be translated as this one long string, potentially, right? That's one possible reference. So now, if you try to have a hypothesis, right, and you only make a mistake in one of those characters, right, one of those letters, nothing matches, right? And that's why you cannot really operate at the symbolic level of the word. I'm going to start the next session after the break asking you to define what a word is, by the way. So you might want to spend the break thinking about what a word is. So clearly, this is not great, right? We cannot be operating at the word level for languages like this. There's this very nice metric called character F-score, which basically splits up everything at the character level and now computes something very similar. The ideal scenario is that you do human evaluation. Okay? You show two translations to humans. Oh, sorry, there's two ways. One is you show the translation to a human and you ask them, how good is it? Right? Is it terrible? Give it a score of 0. Or if it's great, give it a score of 1. Right? Or use a Likert scale or whatever. A better way, if you care about comparing two systems, is to show to a human both outputs and ask them to rank it. And say, hey, is systems one hypothesis better than the other? Or is it the other way around? Or are they equivalent? And that's what we do for the shared tasks. Real quick note of how we might actually evaluate the metrics that we use themselves. Automatic metrics can be very low cost, right? It's very easy to come up with a metric and slightly modify a few things and then claim that you have a better metric. The way that we evaluate whether they're correct is we correlate them with human judgments, right? So we do show outputs to humans and we ask them to rank them. And as long as the automatic metric produces similar rankings to the human rankings between different outputs, right, or between different systems, then we would believe that this is a good metric, right? Because the ultimate judge of what is good, in the end, it's humans. Well, ideally trained translators or, the humans that know how to perform the task. So here's one example of some sort of like slight correlation between a blue score and a human score with regards to how easy it was to fix the output. But then, in some cases, you might end up with systems like these that really don't really show any good correlation between human scores and automatic scores. So people have been doing this metrics task for years. I'm not going to go into the details. They're here for completeness purpose. But the idea is that we have a lot of systems that can produce outputs. We pay a lot of humans every year to evaluate all of those outputs so that we can rank the systems. And then we also have this shared task where people propose metrics, and they rank the systems. The metrics do, and then the metrics that run the best, that correlate the best with human rankings, they become better and better. You might see here that in the most recent WMT, no, that's a lie, to the second most recent WMT, we had, none of these here mentioned blue or comet or whatever that I might have mentioned. You noticed how, a version of blue and character F-score are down here. So we have way better metrics today that correlate with human judgments way better. And all of these are really based on semantic representations at the vector space, right? Using pre-trained language models that have learned to represent sentences in a multidimensional space so that we operate now at the meaning level and score based on their vector similarity. So the idea behind the currently best metric called Comet, which is out of a lab in Lisbon, is that we're going to just train a language model to receive the source and the hypothesis, or the source, the hypothesis, and the reference. And we're going to train it to predict the score that matches the human quality as produced by trained human evaluators of translation, right? So now we train the system to predict the score that the humans would have given. It's a dedicated system to score sentences. It relies on BERT, which you already talked about, or a BERT-like multilingual system to represent everything. And it works really, really, really well for the languages that it supports, okay? Which is the ones that it has learned to represent, the underlying language model has learned to represent. Let me finish real quick on the MT module before we go on to the multilinguality. what we discussed before the break, so far, everything I told you, right, relied on parallel data, right? There was this assumption that a lot of humans, like, maybe professional translators, really just produced translations, right? And we use those to learn, right? And this is a very standard supervised setting. I'm training my neural network or my statistical model or whatever on just concrete examples of inputs and outputs, right? However, there's a lot of language data out there that we could potentially that we could potentially leverage to train our systems, right? So there's a lot of unannotated data, right? There's a lot of text out there in Italian or German or Chinese that we could potentially use to train our empty systems, even though it is not paired with an equivalent, translation in another language. So let's briefly explore semi-supervised and a little bit of unsupervised methods. So the simplest idea that you can potentially think of is the following, right? I told you that the neural networks that we train when we train neural machine translation are still language models, right? They're just conditioned on whatever the encoder produces. So if we have a little bit of parallel data between, let's say, to make it easy, English and French, okay? We also have a lot of monolingual data, just not paired, French, right? And I told you that, again, the models are conditional language models. What do we train language models on? Just data in the language that we want to generate, right? So one thing we can do is potentially, we train a machine translation model on our parallel data. We can use all of the extra data that we have in the target language to train a language model, right? And now we can combine the two. What advantage will this give us? We'll just have a better language model, right? Because the final model will be trained on a lot more French data, and as a result, will be better. So we will be producing more fluent translations, okay, if we combine the two. How do we combine two models? How do we combine two neural models that are trained separately? It's fairly simple. As long as they have the same vocabulary, okay, then what do? Each of those gives you a probability distribution over the next possible words, right? So then you can just combine the two distributions into one distribution and sample from that one, right? That's the simplest thing you can do. If you wanted to, you could combine them before you go into producing the distribution into the logit space, and then make that into a distribution using the softmax. But fundamentally, just combine their two predictions some way, and the simplest way is to average them or add them up. Okay, so this is the simplest way that we can make a semi-supervised translation system that also leverages all of the additional monolingual data that are out there. Right? Here's another groundbreaking way to do this. This is the idea of back translation. And it works as follows. We have some parallel data, as before, and now we're going to use it to train a translation system in the reverse direction of the one that we care about. Okay? And now that we have this trained translation system that goes from French to English, what we can do is we can use it to synthesize possible, synthetic translations for all of these French data that we have here. So we can use our back translation system to create fake English data and turn the whole thing into a parallel data set. Okay? And now we're going to take all of this data and train an English to French system. So, is it a little weird? To who of you is it weird that we are using synthetic data to train, a system, and why does this even work? This actually works very well. It gives you a very nice boost in terms of quality and performance. You think that just makes sense? Yeah? So, yeah, I saw a hand. It's a little weird, right, if you think about it. But here's the crucial point. The output side for the final system that goes from English to French is still human-generated data, okay? that we started with when we produced the back translation. So we still have very fluent output. So we don't mess with our output language model. What we do is we create things that possibly look like English. In practice, the reverse translation system is going to be also pretty good. So even if there's some noise in here as we learn to translate, that's not a problem. If anything, we are making our system robust to these types of noise. Obviously, if this here, the synthetic data, is completely junk, it could potentially hurt our performance, okay? But in practice, even if they're like somewhat okay, then they can, the increase that we get in the amounts of data that we have to train our final system is really, really good. So can we further generalize this approach? So let's say we have parallel data between English and French, and now we also have monolingual data in the source language and monolingual data in the French language, which, sorry for putting them this way, but they're not parallel. Like these two are not parallel. So now for each of these, we can do the following, right? We can train machine translation system using the parallel data on both directions, from English to French and from French to English. And we can use the monolingual data that we have to train language models for both of those languages, right? So we have empty systems going both directions and language models for each of the two. So now we can play the following game. We can take a monolingual sample from English, like a sentence from here, okay? And we're gonna use the machine translation system that goes from English to French and produce a possible translation, okay? We can score this possible translation with the language model that we have in French. And we can score it for its fluency, for example, right, which is what we would get. We can also do the opposite direction, right? We can get a sample from here, translate it back, and score it with the English language model, and keep doing this, basically producing better and better synthetic data as we play this game. Right. Again, I'm just giving you some interesting ideas of how you can use monolingual data. So here's another idea. Translation is supposed to be reversible, right? It's also supposed to be transitive, but that's a different story, right? This means that if I go from English to French, right, then if I go back from French into English with another model, I should end up with the first sentence that I started with, right? Or something very, very, very similar. Or the transitivity idea is that if I go from English to French and from French to German, I should end up with something similar if I translate it directly from English to German, right? So we can potentially encode this as part of our learning scheme. So for example, we can have here an encoder-decoder that takes us from, in this case, Chinese to English. We can have another system that takes us from English to Chinese. And now we can have a loss function that compares the final Chinese with the original Chinese and, do this end-to-end and train the system so that it actually encodes this reversible property for translation. This is called round-trip translation, and you use this for supervision. Right. Another idea that gets closer to what we're doing here. Oh, sorry. Yes.
Sorry. One question regarding your first example, actually, like where
this one.
You said that we can use, let's say, how to combine.
The simplest thing.
Yeah.
Yeah.
Yeah, I think so. Yeah. Yeah. So you mentioned the possibility of, let's say, adding another model and then add the logits, etc. Suppose we are using, let's say, an encoder-decoder architecture, right? Now, we can use the monolingual data with the, let's say, unconditional way. So you can retain the same architecture and just train your decoder with, let's say, empty input, right? With empty encoder.
An empty source.
Yeah.
Sure.
Yeah.
Yeah.
So you can also do that, right? You
Yes,
don't really need
that's
a
actually
second.
what this paper did.
Yeah. Okay.
The thing is, this is strictly worse than using synthetic English, because you're trying to do. It's a little weird to try to use the same, like an empty string as the source, right? Although that paper did it. Turns out, actually, this idea, you can do it even better by just pre-training your model components, right? I told you that your encoder-decoder, the decoder side, is a language model. So why do we have to train it from scratch? We can use all of these monolingual target side data that we have, train it as a language model, right? If you actually want to, you can do the same thing on the source side, and then put the two together in an encoder-decoder fashion, and then teach them with the parallel data to play well together and perform the translation task, right? And that actually works very well. And this is what this says. And then I'm gonna quickly skip through the actual implementation examples that I have here. They're not particularly interesting. You can use them. You can see them at your own time. I do want to share with you the point. Yes.
I was just curious from an overfitting perspective. Does it make sense when? All right, let's try this. Hi. Does it make sense when considering, for example, training a model on monolingual data to also include the relevant part from your parallel data as well, or does this actually hurt performance?
No, it's fine. It's okay.
Is it fine? Is it better? Is it?
I don't really think it matters. It kind of depends. If your parallel data are from a specialized domain, then I think it might help. In practice, for languages where you have so much data, you're still going to end up with a really good language model without even including the parallel portion. So, if you're in a more low resource setting, then possibly it makes sense. But the thing is, you're going to still train on this parallel data. When you do the translation task, you're going to train on this parallel data also effectively on a language modeling task, right? So you will train on all of those in the end. So I don't really think it would make a big difference one way or the other. Okay, so now let's take this to the extreme. I want to very quickly show you an unsupervised translation setting. And that's the example where we're going to try to learn to translate from one language to the other without having any parallel data. Okay? All we're going to have is we're going to have monolingual data in two languages. Okay? And this goes back all the way back to the original ideas that we talked about in the beginning of decipherment. I'm going to skip this. But here's how this will work. And this was a paper that won Best Paper Awards in 2018. We have monolingual data in the two languages. Okay? Now, there's this technique. You guys have talked about word embeddings, right? Yes. Okay. So here's this cool thing. When we move from symbolic units to vector representations, right, that encode meaning, you have a space in English, right, that maybe has vectors that look like this. And let's say you have a space in French where you have vectors that look like this. Okay? And because both of these encode meaning, the vectors for cat and kitten and dog and puppy will all be very, very close, okay, in English. And the equivalent words in French will also have very similar relationships with each other. So here's the thing. We can take these two independently learned vector spaces, and we can fairly easily, with even just 10 words of mapping, we can, translation words, we can learn a mapping between the two and try to kind of align them, okay? So that we can learn a word level translation model, right? If I have a vector space here and a vector space here, and I learn a rotation of these vectors so that this kind of maps, then if I have a French word here, this is my vector, okay? Then I can find the closest English vector and call them translations of each other, okay? It's not gonna be perfect, but it's gonna be okay-ish for content words. So here's what we're going to do. We're going to have this monolingual data, and we're going to use this unsupervised bilingual lexical induction. That's the process of mapping two vector spaces into each other and creating a seed lexicon, right? A seed dictionary between the two. And we're going to synthesize parallel data the dumbest way possible, right? We are going to have word translations from a dictionary that we learned automatically, and we're going to go through each English sentence. For each word, we're going to substitute it with its, closest French word, okay? This is not going to be good translations, okay? Just maybe okay, because English and French are fairly close. And we're going to do the same the other way around. We're going to take all French sentences that we have down here, and we're going to go through them word by word, and we're going to substitute those with the closest English word, okay? So when we do this, we're going to end up now with something that looks like parallel data, okay? Except these two sides are, synthetic, and they're just really bad English and really bad French. Or not even English and French. There's something that looks like English and something that looks like French, okay? And now, nevertheless, I have parallel data. So what I can do is I can train a translation system on it, right? I'm going to keep, for the empty systems that I train, the output side to be the human-generated data, so I can still have on my output, good language models, right, for the decoders. We can also have unsupervised objectives. Basically, these are language models that can be trained to recover from this noise. But here's now the awesome thing that we can do. We're going to iterate through this process, because now what have we done? We have learned a system on this weird, bad French-like data to translate into English. So we're going to take this system and apply it on this French data to create slightly better English, or more English looking like outputs. Okay? And we're going to take this empty system and we're going to apply it on all of this English, and we're going to try and make something that looks a little bit more like French than what we had before. Okay? And we do this iteration, and now we have slightly better synthetic data. Okay? And now you see where this is going. We're going to relearn those models, apply them again, and we're going to end up with slightly better synthetic data again. And we're going to keep doing this. And we're going to keep doing this until, 3-4 times, really, is all you need. And then if you do this for related languages with a lot of data on similar domains, this kind of works. Okay, so I just wanted to show you this. It's by no means like state of the art, right? Having supervision in the form of parallel data is always better. But I wanted to show you this because it's, one, really cool, and B, it really ties very well with the old idea that I discussed earlier, this expectation maximization algorithm, right? We had a chicken and egg problem there where we had alignments and parameters, and if we had either of the two, we could estimate the other. In this case, if we had data, we could learn good models. And if we have good models, we can synthesize good data, right? Unfortunately, we do not have either. But if we start with a slightly decent, initial synthetic data, we can start estimating a model. We can use this to get slightly better data, and then get a better model and get a better data set, and so on and so forth. So there's a theoretical tie between these expectation maximization approaches and this type of approach here that it's I think just very interesting to think about. Yes?
Isn't this going to create a model that only translates words and not phrases?
So here's the thing, right? Largely, yes. But the thing is, if you do several iterations, and if you have a lot of data and languages that are more or less similar to each other, it will kind of work. It will produce usable translations, right? It's not going to be perfect, again, but they will be usable. Okay, so just to summarize, neural machine translation is basically, in my view, I guess, up until 2 years ago when ChatGPT dropped, NMT was the biggest success story in deep learning, right? Basically, it became from a fringe research activity that a few of us were doing to the leading standard method in a couple of years. It was very widely, quickly adopted. Basically, you had all of these insanely big systems built over the years that were, overnight substituted with these neural models that, are faster and much cheaper to train and so on. So does that mean that MT is solved? Nope. Okay, no by any means. Common sense is still hard. There's bias issues. For example, when you're translating from, say, a genderless language like Malay into English, your language model has learned to encode biases, as Dr. Rogers will talk to you about at a later date. Because the world is a biased place, and this is reflected in our data, you end up with things like our models making associations such as nurses tend to be females and programmers tend to be males. Even though this is not actually specified, these will creep up in your outputs. So there's a lot of work on trying to solve these issues. Again, you might have, the model has learned to produce fluent output even if the input is junk. You might have seen every couple of years there's this article somewhere that says, Google Translate spews apocalyptic verses, blah, 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 on this small language where it has only been trained on the Bible. And then you're like, yeah, of course it does. It's been trained on the apocalypse. Of course it will, So point being that, a statistical system would never do this, okay? Neural systems do weird things still. But nevertheless, I'm just putting this out there. Okay, so this is my end of the presentation. I didn't talk to you about large language models yet, right? I'm sure you guys have used ChatGPT, right? Yes, right? Have you used it for translation? Okay, who thinks it's awesome? Depending on your language, okay? So turns out these large language models can be very good for translation as well, at least for translation of high resource languages that they have seen before. They have a very nice advantage that you can just provide in the prompt additional information, right? You can tell the model, translate it as if I'm speaking to a 6-year-old, right? This is not something we can do with a standard translation system. How do I, okay, there we go. Long story short, the most recent state-of-the-art finding is that LLMs are great for translation of high-resource languages. They tend to be very close to the state-of-the-art. But for mid or low-resource languages, they're still not as good as dedicated translation systems yet. This is extraordinary because they're already better for everything in all of the other settings, right? More or less. So that's they have the very nice advantage that they're very controllable. You can tell them, hey, I'm trying to translate a scientific article. Make sure to translate using the appropriate terminology. Maybe here's an example of the appropriate terminology. Here's a dictionary example. Use those words. You can literally, instruct them to do what you want, and they will very likely do it for all of the languages that they are good at, like English, French, Chinese, and so on. So, okay, this is as a side note. You will, in your labs, get to play a bit with LLMs and, with large language models, and idiom translation, so you're going to talk about it more later in the afternoon. Now, I want to talk a little bit about just general things about multilinguality and speech translation. I did ask you that I did tell you before that I was going to ask you to define the word. What is a word when we come back? So, anyone? What is a word? Give me a definition. Yeah?
A sequence of symbols in a vocabulary that has some meaning.
A sequence of what, sorry?
Of symbols in a vocabulary that has some meaning.
That has some meaning?
Yeah.
Okay. How about, are there any properties in those symbols?
Statistically speaking or grammarly, let's say grammatically.
Okay. Okay, anyone have any other definitions? Yeah? Okay. Here's the most common definition that I get. A sequence of characters separated by white space. Okay? Does anyone speak Chinese? Has anyone seen Chinese? Does Chinese use white space? No. Okay. That definition doesn't work. Here's another definition that I hear. A word is something that is defined in the dictionary. Yeah? Maybe. That's also not satisfying, right? Because there's things that just don't exist in the dictionary. Now, I want you to think of when you were learning your first language, your native language. Okay? You probably don't remember it, but you somehow learned it. Okay? Did anyone ever tell you where the word boundaries are? No. Okay? Nevertheless, amongst your people that speak the same language, you would kind of agree, right, on what is a word and what isn't. You don't have to come up with a formal definition, but you would. Okay? So my point here is that I'm trying to say is that we learn these meta-linguistic things about language without needing proper definitions. And these definitions can change depending on who you ask. Like, people don't agree necessarily. So nevertheless, we somehow managed to communicate with each other. And we managed to learn very similar languages. What I want to do now is show you how, assumptions that we make based on the language that we speak can break when we go to another language. Okay? So here's another question for you. How many languages are there in the world that are spoken today? Yes? Yeah? Give me a number. Okay, lady? Yeah? 8,000? Anyone else? 700? 7,000. Okay, you guys are more or less in the ballpark. When I ask the question in the States, I get 50? No, that's bad. I shouldn't say this. So, a linguist in Göteborg, in Sweden, Harald Hammarström, has given the following answer. There's approximately 6,513 languages in the world. Okay, 6,513 languages. Okay. When I ask you how many languages are there in the world, you should have asked me, what is a language? Okay? You might have heard the quip that, what is the difference between a language and a dialect? And the answer is that a language is just a dialect with an army and a navy. Okay? The definition of a language is a socio-political issue as well. Does anyone here speak Serbian or Croatian? These are the same thing. Okay? You didn't hear it from me. Okay? You can understand people from both places though, yes? So if you define the language as, based on mutual intelligibility, right? I and Ion can talk to each other in Greek, okay? We speak slightly different variations of Greek because I'm now influenced from staying in the States for too long and I cannot recall some Greek words, unfortunately. But we can understand each other, okay? So you could argue that we speak the same language, okay? And I could make the same argument for Urdu and Hindi. You might have heard that as you walk from Napoli to Barcelona, you won't realize it as you go, but then you're going to go through like 4 different languages. But from one village to the next, there's going to be small imperceptible changes. Okay? So, nevertheless, there's about more than 6,000 languages of the world, like 6,500 more or less. Now, here's the interesting thing. Any definition of a word that relies on strings is not going to cover about half of the language of the world because half of the language of the world just are oral, which means that they just don't have a writing tradition. Even if there exists a writing system created by some missionary a couple of centuries ago, it doesn't mean that the community actually uses it. So that means that we need to be operating with speech and not with text, right? Which we'll talk about more a little bit in the end, and you'll also talk about multimodal models with Dr. Fernandez later. Now, out of all of those languages, also 40% of them are endangered and vulnerable, or in danger of extinction. What does that mean? It means that young kids are not taught the language. Okay, that's when a language becomes extinct. When you start losing the speakers of the language as a first language. Okay, and all of these dots that I'm showing you here are communities or languages that are endangered. And you need to remember that each of those little dots, okay, represents a different worldview, different cultural values, just different vocabularies, different ways to express different things. They are a different way to represent meaning. Here's another way that I motivate really my research. Humans have 2 ways to pass information to the next generation. Okay, the first one is universal. What is it? I heard something, but I don't know what I heard. What was it? Gestures? No, well, maybe, I don't know. These are not universal, right? What I'm thinking was is DNA, right? For passing information along to the next generations, like 3 generations down. One mechanism we have as a species is, genetics, right? We pass DNA and that encodes a lot of information. The second one we have is language. But we don't have one unique mechanism. We have 6,000 mechanisms, right, that actually end up encoding different types of information. There was a very cool study that showed, that studied languages in the Amazon and showed that each of the communities that they studied, right, a lot of them very, very small and in danger of extinction, they had knowledge about, say, medicinal properties of certain plants that were local to the area. And of course, they could communicate that knowledge in their own language, but that knowledge was not known anywhere outside of that community, right? So language loss is not just, sure, these people learn Portuguese, they can communicate, it's fine, right? It's also a loss of knowledge for the whole human race, okay? Great. So you also need to remember that even if we put languages into clusters, and we have 6,000 of them, right? We also have a lot of variation within each language, right? I've been giving you examples in Italian, but then if you ask the Italians here what type of Italian they speak, well, if you guys are young, you might be speaking standard Italian, right? But then if you go ask older people, you're going to see that there's a lot of variation within the peninsula. So we have regional varieties for all languages, right? No language is a monolith. Every language is a spectrum, okay? And you could even argue that each person speaks a slightly different language from everyone else because we have different experiences. If you think of a language as the probability distributions that you put on words, I'm going to be putting slightly different probability distributions than each of you do in English or in our native languages, right? Then you can also think of the variations of L2 speakers, right? Most of us here are second language speakers of English. And you might have noticed that, Greek speakers tend to add a lot more articles in their English. Russian speakers tend to drop a lot of articles in their English just because their language doesn't use them as much, right? So again, there's this additional variation. And on top of that, you can also think of signed languages, right? Not spoken, not written, signed as a whole other modality that we might want to cover. So the big problem, obviously, of why we do not have language technologies for all of those languages, and we can currently only cover about 100 to 200 of them, especially when it comes to translation, is that we just don't have data for all of these languages. Okay? This long tail here really shows that we don't have, we cannot train language models on 5,000 sentences, right? It's going to be a terrible language model, no matter what we do. So I want to show you a couple of examples of how we can use, however, how can we deal with these problems in this very low resource domain? And there's a lot of different settings. Here's one example. All around the Iberian Peninsula, there's a bunch of, big languages, Spanish, Portuguese, like institutionalized, right? And there's a bunch of smaller ones, like Aragonese or, what is the other one? Mirandese in North Portugal, I want to say. There's also Catalan, also institutionalized and so on. Now, all of these evolved in parallel, right? And they are very similar to each other. You can see these similarities when you put translations across all of those languages next to each other, right? So can we use these similarities to learn without using too much data, right? We have a lot of data for Spanish, we have a lot of data for Portuguese, we only have a little bit of data in Galician, unfortunately, right? So, but maybe, because they look so similar to Spanish and Portuguese, maybe we can actually leverage that. And the answer is yes, right? What we can do is, I have examples here from a shared task. You're gonna play with this in your lab later. I think you're gonna try to do Aragonese to Spanish or English translation. Right? But the core idea is that, we can train a single model on all of these languages, on all of these language pairs. And, because Aragonese or Galician kind of looks a little bit like Spanish and a little bit like Portuguese, we might be able to translate it into whatever the target language is. Okay? That's the general idea. Here's another example. And that's an example from the Indian subcontinent. All of these are like different sentences. Sorry, it's the exact same sentence written in a bunch of different languages of the Indian subcontinent. There's like Hindi, Bengali, Telugu, I think Marathi, Malayalam in there. And all of these are possibly related or unrelated languages that use very similar scripts, right? Each their own, right? Hindi uses the Vanagari, Bengali uses the Bengali script, Telugu uses the Telugu script, which all of these kind of evolved in parallel from the same original, I want to say Sanskrit script, but don't quote me on that, I don't remember. And then a lot of these languages are also kind of related to each other, right? Especially the Indo-Aryan ones like Hindi, Bengali, Marathi, and then the South Indian ones are also related to each other, the Dravidian ones. And as a result, they share a lot of phonetic and orthographic similarity, but they all look very different when you put them in the computer because each of them uses a different writing system. Okay, so what can we do is we can potentially learn to transliterate one into the other because there's character level mappings between the symbols of the alphabet, and then potentially translate between them by effectively almost doing transliteration, or we can then combine all of the data that we have in all of them. There's still issues with normalization and tokenization, right? The way that we might be splitting words across the languages. But this is one example where you have related languages which do not look as similar as these here do. Okay, so that's why I wanted to show you this. The writing system, especially when we're in this space of the world, really can throw things off. Here's another example in English Chinese that has to do with the way that we represent our input. In the lecture before, I basically told you that everything was word level, and we discussed briefly character level. Right? In practice, what we really do is operate at the subword level. Right? We operate at the space between character and word level. You kind of in one of the labs you talked about BPE, right, and subwords and how we can learn this. It's not particularly important how you do this, but the important thing is that, it's not characters, it's not words. Now, if you have this sentence in Chinese has a very peculiar writing system, right? Each character, more or less, corresponds to a concept or maybe a word, right? So it is very, very high resource, but the logographic writing system creates a huge vocabulary, right? You need thousands and thousands and thousands of entries in your vocabulary just to cover all of the possible characters, right? This is very different from what we have, in any other writing system where you can represent everything with a few dozen characters. So the other thing is it doesn't use white space, so it's not straightforward to figure out, how should you split this, right? Should you do character by character? But then we also know that sometimes pairs of characters come together to form a unique meaning. So you cannot just do character by character. Nevertheless, if you do character-based decoding for Chinese, it tends to be better than doing subword, or there's ways to kind of like try to define words in Chinese that I'm not going to cover, but basically character-based decoding can help. But then you could also realize, these characters do encode information in sometimes in the components that they have. So, for example, you might be able to see here, I don't know if it's big enough, but there's this character that is, I think it means run, that is comprised from the word for horse and this phonetic ideograph that basically describes how you pronounce this character. There's also the word pool, that is comprised from the semantic ideograph for water, and then you have this same phonetic ideograph and you see why the pronunciation is very, very similar, that tells you how to pronounce this one, right? So maybe if we decompose this information, right, these characters, into the two, the semantic and the phonetic ideograph, we might be able to model Chinese better. And turns out that this work does this sub-character level information tends to somewhat help. In fact, you could even go further down and realize that, today people type the Chinese characters by typing representations of parts of them. And you could say, hey, maybe that's a meaningful segmentation to potentially do. And there was this paper that showed that if you use this, it can also kind of potentially help. The reason that it does is it really reduces the space, the vocabulary of the models, so it makes the problem easier to model, right? Translating into or out of Chinese is still as hard as it was before, but it makes it a little easier for our current models to deal with it. Here's another case study. Arabic. Does anyone here speak Arabic? Which Arabic? Levantine one, okay. So here's the thing. A lot of research has focused on modern standard Arabic, okay? Which is not a thing. No one actually speaks it. It has been designed by the Academy, the Academy for Arab Language, I want to say. It's a name like this. It's very similar to what you would hear, say, in Al Jazeera, right? And where most of our data comes from, really. But, you know, it's not what actual Arabic speakers actually speak. In practice, all along the Arab world, you have different vernaculars, right? Different versions of languages based on Arabic, that, for example, in Tunisia and Algeria are also have a lot of French loanwords because, you know, colonialism. Or, you know, Egyptian Arabic is slightly different, and this is different from North Levantine or South Levantine, and this is different from Gulf Arabic, right? And in practice, people from the West will kind of understand people from the East. People from the East will not really understand very well people from the West. So really, what you really need to do if you're trying to model Arabic is you need to get data from each of those communities and potentially try to combine all of these things together. Again, fun fact, in the US, when they train diplomats to get deployed in MENA, right, the Arab-speaking world, they don't teach them any specific Arabic out of these. They don't teach them modern standard Arabic because, again, no one actually speaks it and it sounds awkward to read to actual speakers. They teach them a version of Arabic that tries to be the less offensive to all of these people, which I thought was really funny. Yeah, that concludes the fun fact. Okay, so the other thing that Arabic does is it doesn't write everything. Typically, they only write, not typically, they only write consonants, right? And the way to pronounce the word is inferred from the context when you write it. Another thing, and that happens is all of the words that share the same root, that effectively are the ones that have the same consonants, okay, will be written the same, but they will be pronounced differently in different contexts. So the different versions of the verb to write, okay, like if you want to say I write, it will be some word, okay, which will be written with the equivalent characters for KTB, okay, because these are the three letters that make up the root. If you want to say he wrote, you'll have different vowels in there, but on text, it will still be KTB. Okay, so what you have is a very abstract representation on text, and you somehow, this makes modeling much, much harder, right? So a lot of the approaches from the past, you know, from in the 90s and the 2000s, they first did morphological analysis on the text. They tried to infer grammatical information based on the context, and then provided the roots and the grammatical information as part of the source to potentially translate that into English. There's other solutions that try to handle these dialectal variations that I talked to you about, where they might have first trained a neural machine translation on all Arabic data that they might have, all the way from Morocco to Iraq. But then they will also have specific models for each of those varieties. And then in order to properly translate, you know, for example, Egyptian Arabic, what will they do? They will have some input that will be some sort of Arabic, right? They will perform dialect identification to hopefully correctly identify it as Egyptian. So then they will go to the Egyptian model and then combine the outputs of the Egyptian specific model with the generic Arabic model and produce hopefully a good translation of that. Okay, then other languages like Finnish or Turkish, they have very complicated morphology, at least when you compare them to like Indo-European languages or English or Germanic ones, okay? Basically what this means is they will add a lot of grammatical information to the same word and end up with really, 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 really long words that, in English, they could be the equivalent of like a sentence. It's like the Azerbaijani example that I showed you before, the really, really, really long one, right? So what you need to do in these cases is figure out what are all of the morphemes that have been added to the word and appropriately split them so that you can translate into English, right? And that's called segmentation. And it turns out that, if you do this segmentation in a linguistically informed way so that your segments actually match what are the actual meaningful units in the language, you can do, it doesn't sound too weird when I say it this way, you can do a lot better, right? Rather than having an automatically learned, uninformed segmentation. Okay. So a related question is, okay, I told you that there's related languages that you might want to use and train a system on several languages that are related, right? So how can you choose which languages to use if you ever want to train a system for a specific language? So you could use your intuition. You could say, I don't know, Portuguese kind of sounds like Russian, right? I'm going to use Portuguese and Russian, right? It could be okay, it could be not. You could use geography, right? You could say, hey, these languages are spoken in the same region. It might mean that they have evolved concurrently, they might be related to each other, or they might have exchanged a lot of information through the centuries, so maybe I will use them. They have some similarities. But again, thanks to colonialism, this can be very misleading, right? Afrikaans is basically Dutch spoken in South Africa, which is not related, typologically to any of the other languages spoken there. Or you could actually, turn to linguists and, use typological features and basically, say, hey, linguists have already identified that, all of these languages are part of the same language tree. They are related to each other. They evolved from the same common ancestor, very likely. So, we will use those. And it turns out that if you do that, you can actually do fairly well. Now, I want to switch gears and talk about multilinguality. Right? You have already talked about BERT, and we've talked about LLMs, and you already know about this. And there was this trend in NLP in 2018. We're going to use BERT for everything, right? And then it eventually became we're going to use XLMR, we're going to use Electra, GPT-2, then Chinchilla, and now it's like ChatGPT for everything. Okay? Now, that's okay, right? These models do work better from than what the previous ones did. And if you want to cover a lot more languages, what people did is just train this one single language model on all of them. Okay, take all of the data that you can off of the internet. They won't be balanced, right? Notice that this here is a logarithmic y-axis that shows you the available data on a very large internet corpus. And obviously, English has an order of magnitude more data than any other language. The next one is like Russian and Spanish and German and French. Chinese is somewhere there as well. So what people typically do is upsample the low resource languages that are over there at the long tail, and basically sample training examples from them more often, so that you see enough batches of them, you do enough updates in those languages. And what you will do is just train a language model the exact same way that you did for English on all of these languages at once. Okay? I call this, so let's say we want to basically go beyond the top 100 languages for which we actually have some data on the internet, right? A decent amount. And for these top 100-ish languages, you don't even need to build monolingual models. You can just take whatever language data you have of the internet and train a decent language model on them. So the current approach has been, we're going to make large language models multilingual. Effectively, what we're going to do is we're going to train them on these 100-ish languages for which we have a lot of data. And then we're going to hope that these models are going to generalize to everything, right? And obviously, you can kind of see the problem here, right? The problem is that the languages that we train on are sociopolitically dominant. They have a long-standing writing tradition most of them using the Latin script. They are fairly standardized, right? So most people, when they write them the same way. And we have enough data for them. All of the other languages tend to be local, which means they don't necessarily have institutional power, because if they did, they would be on the upper set. They're predominantly oral. Even when they're written, people don't necessarily write them in a standard way, okay? And whatever written data we have is very little, okay? So these are the types of problems that we have to deal with when we deal with low resource languages, extremely low resource languages. So I call what GPT-4 approaches do incidental multilingualism, right? We just train on all of the internet. We happen to get data in 300-ish languages, and maybe we have learned something in some of them, but it's not multilingual by design, okay? Sorry, something happened to my iPad. Just a second. Oh, I know what happened. Or you could try and be a little bit better about it. You could explicitly collect data in many, many languages and upsample, right? This is even better than what GPT-4 might be doing, but nevertheless, this is still not satisfying, right? So how do we get data for our current large language models? The answer is internet crawling, right? You might have seen a project named Oscar out of INRIA in Paris, where what they do is they crawl the internet. They tag every document that they find, every page that they find with a language using automatic language identification. And then they currently support 166 languages, and then they periodically release more and more data because, there's more and more content put out on the internet for these languages. Now, if you actually audit these web-based, like web-crawled multilingual data sets, what you find is that some languages are extremely low quality. One glaring example from this paper was that 100% of the data that was tagged as Neapolitan, the language spoken by about 2 million people around Napoli in south-ish Italy, okay? All of it was really Italian, written in a cute way where people write YouTube comments where they put spaces between every character. Have you seen this? Where it's like, you just put spaces between every character and then maybe you alternate uppercase and lowercase stuff. And the automatic language ID said that's Neapolitan. And, that was presented as, here's your Neapolitan data set. You train and you can do stuff. You can do part of speech tagging in Neapolitan. You can translate Neapolitan and all. Right? But 100% of that sample was just cutesy YouTube comment Italian. So basically, my argument is that drinking from the internet fire hose is not particularly great for the low resource languages. Before I go to this, here's another problem that I don't have a slide for incidental multilingualism. You have used ChatGPT, okay? Who has used the paid API? Like some people. How do you get charged? Huh? Okay, I'll tell you as an advisor, okay? You get charged by the token, okay? Each token costs a fraction of a cent, right? Now, here's the problem of incidental multilingualism. You have talked about how you need to learn a vocabulary over which you define your language model, right? And you learn this over subwords. Most of the internet data is English, okay? So if you have a sentence like, what is the capital of Morocco? Okay? This is going to be segmented through, OpenAI's ChatGPT interface into something like 7 or 8 subwords, like what is the capital of Morocco? ? Okay? More or less. Maybe one of those might be split a little bit, but it doesn't matter. Like 7 tokens. So you will be charged 7 times whatever the cost is per token. If you ask the exact same question in Greek, right, this will be split, will still be, 7-ish words, Greek words, But the ChatGPT tokenizer will split it at the character level because that's what it does in Greek. Because Greek internet is a tiny fraction of overall internet. Greek uses its own alphabet, right? Its own writing system, which makes it unique to it. So it doesn't get represented very well among all of the world's languages, right? All of the writing systems. And what you end up with paying is 40 times the cost of the token. If you ask the same question in Telugu, you will end up paying even more, okay? Because Telugu characters are actually, each character is split into 2 tokens typically, right? So there's already inequality introduced by just tokenization, right? And in terms of access to technology. Yes?
Yeah, I just wanted, I'm not sure if you're going to get back to this, but I noticed another problem relating to this Croatian-Serbian similarity that you already mentioned. GPT is sometimes finding it hard to distinguish them, especially when you write in anything that's a bit non-standard, because of course, the lower amount of data. But even if you write standard, it's really common for the model to switch them. And because kind of the biggest difference, let's say, is just one way of writing one like phoneme. It's either with J or without, let's say, very simple thing. It can easily and will easily switch them, which basically makes it the other language in written form.
Yeah.
So I think that's another big problem of incidental multilinguality. If they're not trained as well to distinguish the languages, it's going to be really easy to mix them up for similar languages.
Yeah, absolutely. Yeah, you're not wrong. There's actually a paper accepted to this year's EMNLP, which is one of the top tier conferences in NLP, that is already available out, and it deals with this language confusion in large language models. It's out of Anthropic, I want to say. And in my lab, we did some work at some point where you prompt an LLM with something in English, let's say, but that mentions an entity in another country. Let's say you prompt it with in Buenos Aires, and you ask it to continue. And even though this is English, because in isn't really used in Spanish, it will still continue in Spanish. Sometimes we would prompt it in Bangla, and it will continue in Arabic. Sometimes we would prompt it in Japanese, and it will continue in Chinese. It's a fairly common thing, and that's because we don't train the models with a language tag, right? We don't tell them, oh, here's a sentence in Japanese, do language modeling on it. We just give it data, right? And we rely on the model to figure everything out, and sometimes it doesn't. Okay, so what we have done in the past is we have worked with communities to build data sets for them. For example, we did some work in Zambia to build data sets for these severely underserved communities. There's 30 million speakers of the languages here in Zambia, the Bemba and Tonga and Tumbuka, for which there's like no data out there, or very minimal ones. And with a little bit of money, think like $50K or $60K, dollars, you can build a very good data set to start building language technologies for them. And this is an image from Chile, where I worked with an indigenous community to build language technologies for them. Another thing that perhaps might be of interest is that for a lot of the languages that we say that we don't have data, there's an asterisk there. Data does exist, just not in computer-readable format. Maybe you have books, maybe you have magazines and newspapers in print. Maybe you have scans of those in image format. So the question is, can we use them to train language models? The answer is not yet, right? They're not text, which is what we train language models on, but maybe you can do OCR on them, optical character recognition, to render them into text and then potentially use that to train models. Or you can maybe not get tons of data that is very low quality. Maybe you can get small data that are, however, high quality. We did this project where we went to a publishing house, well, actually 2 publishing houses that provide children's stories. that are human translated and verified for 350-ish languages. And this is a very specialized domain. It's very simple, right? It's children's stories. But that way we are sure that we have correct data in more than 350 languages, right? Now, here's what happens when you suddenly get access to high quality data in that many languages. You can try to do the simplest thing, like language identification, right? You're given a sentence and you're trying to predict what language it is in. And then you go to the state-of-the-art models and then you get these accuracies, right? When you expand to that many languages. The existing LangID models are just terrible. So I just wanted to show you that, we're not nearly close to being done with NLP, right? You might be interested in doing mathematical reasoning with LLMs in English, right? But there's tons of communities, thousands of communities that still have their most basic needs not met, from not having a keyboard to not having, like predictive text to not having translation for their languages. Not that everybody needs those, but nevertheless, they should have the option if they want to. Okay, now I also want to talk a little bit about dialects and remind you that languages are not monoliths. This is my favorite map of Italy, but this is not just Italy that is weird in a way. This is the map of France and the different dialectal regions. This is the map of Greece and the different dialectal regions. It doesn't matter how small you go. Netherlands of the 4 million people still has differences in the different dialects, and even smaller languages will also be continuums. So we did this work where we collected a lot of NLP tasks in a very standardized formats, from dependency parsing, syntactic analysis basically, to NER, like the ones you talked about yesterday, to translation that covers a lot of variation for many languages. So for example, we have Basque, right? I don't know if we have anyone who speaks Basque, but we have the same sentences in 21 Basque varieties. So we can benchmark translation as things change a little bit. And turns out that our current state-of-the-art systems, the best translation systems that we have, the moment you give them a little bit of a slight variation that is, dialectal, it's something that people would largely understand. Maybe, not if you're from the north of Italy and you're speaking to someone from the very, very, very south. But, nevertheless, these are languages that we should be able to cover. When you benchmark state-of-the-art systems today, right, you get, here's an example from Italy, you get really high quality if your Italian is close to standard Italian. Modern standard Italian is based on Dante, really, which is a version of like Roman and Tuscany Italian. Okay, the further away you go, the worse the system becomes, right? If you go up in the north or if you go down south, the model gives you worse and worse outputs. The same with Switzerland, right? Again, rich country, we should be able to cover it. Turns out Swiss German is weird. No, let me rephrase. Swiss German is very different from modern High German from the north, and the closer you are to the German border, the better your variety is going to be covered by existing systems. Okay. In fact, the Swiss government has poured a lot of investment into actually building data sets of Swiss German so that we can actually build systems dedicated to Swiss German, so that we don't have to rely on High German, because we shouldn't. So I also want to give you an example of what happens with not even just Italian or Swiss German, which are still majority languages in there. Here's an example of what happens in multilingual communities. And by the way, most people in the world, A, are multilingual, right? They don't only speak one language. And B, they operate in multilingual communities, multilingual scenarios in their day-to-day life. So here's an example from Iran, okay, where you have a dominant language, Farsi, right? It's what's used by institutions, by the media, by the government, and so on. But nevertheless, there's about a dozen other languages spoken in the country. There's Kurdish in the west and in the north. There's a little bit of Arabic close to the border with Iraq in the south. There's Luri, there's Raji. There's other smaller languages around the Caspian Sea, like Gilaki and Mazandarani and so on, right? Now, here's what happens in the actual data from these communities, right? They have to operate within a multilingual environment where they face pressures from the dominant language, in this case Farsi, right? So what they end up doing is, depending on the context, they might be getting influenced from Farsi, right? The same way that, I'm used to teaching NLP and giving lectures in English, okay? If you asked me, even though I could probably try, if you asked me to speak and deliver a lecture in NLP in Greek, I would really struggle, right? And many of you would probably struggle as well. Mostly because you probably don't speak English, Greek, sorry. But that's not the point. You get what I'm trying to say. So, turns out that what happens is you end up. Oh, by the way, all of these languages here in Iran, they use the very same Perso-Arabic script with slight variations. Each of them, none of them is exactly the same as the others, okay? So I just want to point this out. But nevertheless, they all look kind of the same. But what ends up happening is that the dominant language will influence the minority one, right? So when people write, especially these minority languages, they get influenced instead of using the grammatically correct conventional writing, because all of these languages do have a writing tradition, they do have grammars, right? They're not necessarily taught in school, unfortunately, again because they operate under the dominance of Farsi or Urdu in Pakistan or Arabic in other places. They end up in practice, right? When people write them on the internet, they use unconventional writing where parts of their writing are influenced by the dominant language. In this case here, we have highlighted things that are actual Farsi and not Gilaki, for example. And then this really, really messes up our models because actually we built this case study. We covered all of these languages that use the Perso-Arabic script. And first of all, again, if you try to do language identification, you get terrible performance by any existing toolkit. So what we did was we trained our own on real-world data, right? Not the idealized conventional writing ones. That is actually okay. And then we also noticed that, hey, there's some languages that get confused very often with each other. So then you can potentially build smaller models to distinguish between them and not just have one model that tries to do everything. That's maybe another interesting takeaway for the future. So yeah, this hierarchical model can get even better. And then I want to show you this effect of this unconventional writing, which does not affect people, right? Because they do speak these languages. They speak both languages. They all understand each other. But then when we try to do LangID, on clean data, we will get 95%. But then when we combine clean with a little bit of noise, right, at different levels, quality really, really degrades. The moment you train on a little bit of real-world data, quality stays more or less the same. Still not as good as when you have clean data, but it's still acceptable. We also have the same problem, not on just language identification, but also on machine translation. Let's say you try to translate all of these languages into English, right? Let me show you. Here I'm going to have results with blue on Sindhi, Sorani, and Kashmiri. Okay, and these are the quality. This is the quality of the systems when you give them clean data, right? They're, let's call it pure, for lack of a better word, Sindhi or Sorani or Kashmiri, and you get usable outputs. The moment you give them unconventional outputs, unconventional inputs, you get terrible outputs that are not usable. If you apply a normalizer to turn the unconventional into somewhat conventional, you can kind of recover a little bit of the lost accuracy. Okay. Nevertheless, this is still pretty much an open problem. And it's not a problem just for languages of the Perso-Arabic script. It's a problem for any minority language. Okay, so here's the last part that I want to talk about, is about the need to handle speech input. As I said, most of the world's or about 50% of the world's languages are predominantly oral. I firmly believe that we need to move away from text-based NLP. We have kind of already figured out how to do this, right? Just train a language model to do everything, as long as you have enough data. And if the language does have a writing tradition, if not today, in a couple of years, you will have enough data because more and more people get access to the internet by the day. But for many of the world's languages, we need to be able to handle speech, and the same goes for handling dialectal variations. Dialectal variations do show up a lot more in speech than they do in text, right? So real quick, there's a whole side story to the story of machine translation that is text-based, and there's this other side story of speech-based translation, okay? And before end-to-end models, because as you might imagine, today everything is done with neural end-to-end models, just like everywhere else, we had some proofs of concept where you had basically, I'm going to skip this, but you had, I'm going to skip it. Let me find what I had. Let me tell you first about why this is a challenge, and much more of a challenge than text-based stuff. Speech is awful, right? I don't know if has anyone ever looked at like a spectrogram or like, a wave audio file? We can have all of us here say the exact same sentence, okay? And then visualize the spectrograms, and they would be very different from each other, right? And that's because we have, different vocal tracts, right, with different lengths and different accents, and we use slightly different lengths for how long we take to pronounce each word, and we will make different pauses, and so on and so forth, right? So even though if I asked you to write one sentence, you would all write the same thing, when we move to the speech domain, all of these things that look the same in text will look very different, okay? On top of that, you have things like, ambient noise that can be encoded by microphones. You might have the equivalent of like the cocktail party problem where you have multiple people speaking to each other, and yet people can identify and pay attention to the conversation that they want to, but the moment you represent all of them into one audio file, good luck doing anything with it, right? If you want to, model it. So there's a lot of challenges with speech. On top of that, text is so clean, it's so nice. Speech has disfluencies. People, hesitate every now and then, like I just did. They add discourse markers in between, which, we don't really write them down. Not to mention that if you think about it, do you ever denote punctuation marks when you speak? Question mark? You don't, right? Nevertheless, you kind of figure it out, right? And there's this lie that teachers tell you that, a short pause is a comma and a longer pause is a period. That's a complete lie, okay? So speech, even when transcribed, is very hard to make it look like text, because people speak in continuous streams. They don't speak in nice, well-crafted sentences unless they are like a very, very well-gifted orator. So yeah, no punctuation is a problem. Now, you could say, well, I'm going to do that. I'm going to take speech, I'm going to make it look like text by applying automatic speech recognition, right? We know how to perform automatic speech recognition. It's another encoder, it's another sequence-to-sequence task, right? We have a sequence of audio frames. The output is a sequence of words. We just have to have a better encoder to handle the audio. And hope that, we're going to convert the audio into text, and then we can translate it. The problem is that you did this conversion automatically, so it's not going to be perfect. And these errors tend to propagate and get amplified when you perform translations. Okay? The reason is you train your model, the translation model, typically on clean data, right? So the moment you give it data with noise or errors, it doesn't know what to do with it. The same way that the clean data trained Gilaki and Mazandarani and Sorani translation models did not know how to deal with Gilaki plus Farsi or Sorani plus Farsi data. And in the end, you could also say, wait, maybe I'll just collect end-to-end data, right? I'm going to have speech in English, translated professionally in French, and I'm going to train an end-to-end model to do this. That does work, okay? It's not weird as long as you have enough data. The problem is we really don't have, by any means, as much data as we do in the text domain. Right, okay. This is another challenge that is related to online speech translation, that basically, have you ever observed an interpreter do their job real time? They translate while the other person is speaking, okay? This is not the same as being given a nicely finished text or sentence that you can get to translate as a whole, okay? In fact, there's like tricks. That's why people go to school to become interpreters. There's tricks that you learn in order to be able to handle this and to be able to do this. And our models are really not great at doing this well, yet. Okay, so what was the traditional cascade approach? It was the approach where you would have some audio, you would transcribe it with speech recognition, and then you would feed that into a machine translation model. Okay, this is the traditional approach. The end-to-end approach that has become, I'm going to take this back. It's one of the approaches that we're studying to this day. It's not clear whether it's better or not than the other. Is one that tries to go directly from audio to the translation. Right? Notice that these are still encoder-decoder models. As long as you have enough data, you can train them. Okay? Right. Okay. So what's the deal with end-to-end speech recognition? It is very much the same like what you guys have seen before. You know, the encoder-decoder with attention, you represented the input with some embeddings, you had some encoder, it doesn't matter what it is, you obtain some intermediate representations, and then when you have your decoder, you perform your attention while you obtain an attention matrix, you use it to obtain a context, and then use that to predict the next word, okay? The only thing that changes when you do speech translation with neural models is that now you have an audio input model, where you now represent the audio with a bunch of vectors, and you do the exact same thing, okay? And you use this to predict the next word, one word at a time. Okay, so these days, the only thing that changes, and where most of the research is on how do you do this well for audio, right? Because we discussed how we were going to do this for text. It's fairly easy to decide where the boundaries are, okay, barring any philosophical questions about what is a word. For speech, what we typically do is just create small overlapping segments and then try to abstract them away and make it shorter. Raquel will talk more about this later. Okay, sorry, let me go to the next one. Okay, so another thing that we do today is pre-training. And I want to very briefly talk about the recently released seamless M4T model out of FAIR. Not because I like Facebook or whatever, or Meta, it's really good. And it has some very nice ideas. So what did they do? So they have a large pre-trained model, text-based translation, that has been trained on basically as much parallel data as they could find on the internet through either, identified parallel data or mined data. Mining is the process where you're given a sentence in one language, and then you search the internet and to find a match of another sentence that is a potential translation of it. And you do this in semantic space. You represent the sentence with a vector, and then you try to find the vector in another language that is close enough so that hopefully these two are translations of each other, right? So they have a pre-trained text-based encoder-decoder translation system. And now they want to add speech to it. What they do is they take a pre-trained language model that is trained on speech, right? The exact same way that we trained BERT for text, we can try to do something similar with audio, okay? Conceptually, you can think of it as I'm still going to just mask out parts of the audio and try to predict it, to predict the missing component, right? The only difference is that we don't actually try to predict the audio, we try to predict an intermediate representation that is ideally close to a phone or a phoneme, right? Which is a representation of an actual sound like k or p, okay? And then what do is they put these two components together and they train them with whatever little data you might have that might tie the speech modality with the output translation, or the speech and the transcription and the translation, and train them all to kind of like play well together to produce a system that can handle both speech input and text input, okay? In order to translate. They have this extra thing where it then takes the output translation and turns it back into voice, so they can do speech-to-speech translation and not speech-to-text translation. So yeah, I guess I had this point about data mining here, where if you think about it, comparatively, we have a lot of available data to perform machine translation. That is parallel data, text-based, between two languages. We tend to also have a lot of data for transcription. We have audio and then the accompanying transcript for many languages. For direct speech translation, where we go from audio in one language to text in another, we really have a tiny bit of data. Okay? Sometimes we might not even have transcripts. I've worked in a language in Mali called Tamashek, which people just don't write. So we have to operate on audio in Tamashek to translations in French and try to build something with 18 hours of audio, which is nothing compared to what we have for English, where we have thousands and thousands of audio with transcriptions and potentially translations. So this is what mining kind of looks like. In the audio space, you might have a segment of an audio, and you tag it with language identification, which, remember how terrible language identification was? It can be even worse when you operate in audio, even in high-resource languages, but nevertheless. So we're going to have some Arabic audio segments, or tagged Arabic audio segments, some tagged English, some tagged Vietnamese. They actually over-segment them to even smaller sentences, so they're between 1 and 3 words long. And then what they do is they're going to represent them in some shared representation space with some model. It doesn't matter what it is. It's a model that has learned to represent both text and audio into a shared representation space. So everything becomes a bunch of numbers. Okay? And then they're going to try to find pairs of vectors in different languages that are very close to each other. And when they do, they're going to call these translation pairs, and they're going to put it in the training set. So this is what they did. They aligned speech to text and speech to speech data, and then they use all of these along every other available resource to train this system, which can now translate speech or text from about 100-ish languages to another 100-ish languages, okay, which is pretty cool. Again, by no means perfect, okay, especially for the lower resource languages, but still pretty cool. Right, and I guess this is the description of these representations that put together speech and text in the shared space. And yeah, I don't have any explicit results, but it's actually pretty good. Okay, I'm going to skip this. It's not particularly important. Oh, and I think that's all I had for you today. Yeah. Okay, I'm in time. Great. We can take questions, of course, and you're going to hear a lot more about speech and other modalities from Dr. Fernandez, either tomorrow or in 2 days. Wednesday.
Sorry, before taking some questions, and thank you, we will also take a family photo of the entire school before the lunch break. So we're going to take questions, but then don't leave. We want you all to come up here for the photo, and then you'll have lunch, right? So, questions?
Yeah.
Hello. Hi. I have a question. You're here in the back, last row. Thank you very much for your talk. Very interesting. These projects in the community in Zambia, I think it was. Do you know the names of the publications? I wanted to look it up.
The papers?
Yeah.
You can. They were on the slides. They're kind of tiny, so you can find them. I'm pretty sure that if you search for my name and Bemba, which is the major language that's spoken there, then you can also find it.
And the slides are uploaded in the GitHub probably or somewhere, right? Or?
They should be, right? Yeah. if you go to the website, then there's two sets of slides, at least for mine,
Just on the,
for the
on the
MT and
school's
the
website,
multilingual.
there's a tab that says presentations, and all the slides are already there.
Brilliant, thank you.
I forgot to tell you about this, that I get asked fairly often the question, how much data do you need, for a new language? The answer is, I don't know. But almost always going to be as much as possible. But if you do have related languages with a lot more data, then this can help. You might not need as much. That's the best I can tell you. Yeah.
Hi, thank you for the
Hi,
talk.
yeah.
I wanted to ask, do you think that monolingual NLP surveys could give room for more data? So not multilingual surveys or not surveys, so monolingual, focused on a specific language.
What about monolingual works in these smaller, lower source languages? So that's a tricky question. So we do know that scale helps. Okay, the more data you have, the better. And we do know that scale only works, like LMs at this stage that we have now, right? Only work after a certain threshold-ish. Like, I don't know exactly what it is, but it's big. So at the same time, we do find that multilingual models can generalize across languages, right? So you can take an LLM that has learned to perform certain tasks in English, okay? And it has seen training examples of that. It also is a good-ish LM for, say, Greek or Italian, okay? But it has never seen how to perform a certain task in these languages. But these models can now generalize and learn to perform these tasks in the other languages because they put everything together in a shared space. So there's definite advantages to multilingual systems. The biggest being, you need less data in any given language. You could argue all languages share at least some level of similarity. There's no language without verbs, right? We all operate in the same planet in largely fairly similar contexts. There's certain certain parts of the semantic space that is shared for all humans. So again, we can really help one language from mapping into that shared space. Unfortunately, there's no good answer, but if you have enough data to train a monolingual one, it will tend to be better. If you don't, you're almost always better off with, multilingual approaches. Yeah.
I wanted to refer back to the Quality Atlas paper that you showed. I think they survey 5 data sets or so in there, and they see that different data sets demonstrate different problems like ungrammaticality or just purely language mislabeling and so on. And it also highly depends on the domain, like data from Wikipedia is slightly better. So on one side, I think you could pick just a slightly better data set. We also rarely train on just one single data set. We usually take a lot of them. And on top of that, we also apply different sampling techniques from those data sets to kind of like ensure the balance between the languages for a multilingual model. And then you see that, okay, multilingual BERT generalizes fairly well, for example. Do you think that those like tricks with the sampling or just basically this can be mitigated, that the one single problematic data set is not really an issue?
Let me see if I understand your question. The question was whether these audits are actually good enough or if there's like a better way to ensure the quality of our data sets?
Whether those minor mistakes actually matter at scale, yes.
Very good question. So the problem is for many of the world languages, that's all the data we have, right? So if they matter at scale, I don't have an answer. It's just, you could argue that, maybe we have a lot of good Napolitan data in this example, right? That is just labeled as Italian, but nevertheless, it's still modeled, right? Because it's included in the data that is labeled as Italian, and maybe that's why the model actually can perform tasks when prompted in Neapolitan. That's fair. But I have a counterexample. Have people heard of the Scots debacle? So the story goes, there's Wikipedia, right? And Wikipedia is available in many, many languages of the world. And one of those was Scots. It's not Scottish English. It's not Gaelic. It's a language spoken somewhere in Scotland. I don't remember where. I'm sorry. I'm terrible. Now, there exists a Wikipedia for Scots, okay? And Wikipedia does have, checks. There's moderators and stuff like that. People, downloaded Wikipedia and trained multilingual BERT, for example. It's entirely trained on Wikipedia, right? Turns out, all of the Scots Wikipedia was written by an American teenager who thought they were doing a good thing by, paraphrasing, malforming English. They had studied something, I think. They weren't just doing something bad, malicious. But we thought we had models for Scotch, and what we had was models of a 16-year-old from somewhere in Kentucky. And that was all the data that we had available for Scots, right? So that problem did not go away with scale, right? So. We have to stop here. Okay, yeah, we have to stop. Let's come take a photo.